Hello there, and welcome back to the Sleep Science. Tonight we're floating far beyond the familiar, past the swirls of city light and weather satellite loops, into the deeper ink of the cosmos itself. You might think that space is by definition mostly empty, but what if I told you that our little patch of universe is even emptier than average? You are right now living inside a cosmic hollow, an immense bubble of near-nothingness called the local void. It sounds dramatic, I know, and fair warning, you probably won't survive this one if you're allergic to existential dread. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tell me your location and local time down in the comments. I love knowing where in the world everyone's listening from. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start by picturing the night sky not as a dome above your head, but as a slice of a much larger web. Each point of light isn't just a star, it's a galaxy. Hundreds of billions of stars bound together and strung across the universe like glowing pearls. Yet between those strings lie oceans of darkness, cosmic deserts where galaxies are scarce and gravity stretches thin. That's where we live, on the outskirts of a galactic island chain, beside one of the biggest empty basins ever mapped. It's an odd feeling realizing that your cosmic address includes a massive nothing. Astronomers call this the local void, and its estimated diameter could exceed 300 million light-years. Numbers so absurd that they're almost meaningless until you translate them into sensation. If you could somehow travel at light speed, and assuming you packed snacks for a few 100 million years, you'd spend the entire journey surrounded by almost nothing, an occasional lonely galaxy drifting by like a shipwrecked ember. The idea that our Milky Way hugs the edge of such emptiness is both eerie and beautiful, like living on the rim of a silent crater that stretches across eternity. You drift in imagination toward that darkness, the stars thinning until even the faintest glimmers fade. The temperature drops toward the cosmic background, 3 degrees above absolute zero. In that quiet, photons left over from the Big Bang whisper across your skin. They've been travelling for nearly 14 billion years, and most have crossed regions denser than ours. Here in this cosmic pocket, they move more freely, fewer obstacles in their way. The emptiness amplifies their loneliness. The funny thing is, we didn't always know we were standing in a cosmic hollow. For most of human history, we thought the universe was a fairly even spread of stars, like a sea of sand grains. It wasn't until the late 20th century that redshift surveys, maps built from measuring how galaxies' light stretches as the universe expands, began to reveal the true landscape. In the 1980s, astronomers using early computers noticed vast patches with hardly any galaxies at all. One of those yawning gaps surrounded us. Imagine the embarrassment. The cosmic equivalent of realizing your house sits at the edge of town, next to an endless parking lot no one wants to use. Still, that realization changed everything. Suddenly the universe looked like a giant foam of bubbles, filaments and nodes, what scientists now call the cosmic web. Where gravity had clumped matter, you got the bright strings of galaxies. Where it hadn't, you got voids, immense underdense regions like the one embracing our Milky Way. Historians still argue whether the first real map of the local void came from Brent Tully's work in the 1980s or from later redshift compilations in the 2000s. But either way, the void became more than a theoretical gap. It was a real address on the cosmic GPS, and it was ours. There's a small irony here. Human beings have spent centuries terrified of being ordinary, first dethroned from the centre of the Earth, then from the centre of the solar system, and finally from the centre of the universe. And just when we'd come to terms with being cosmically average, the data whispered, actually, you're in kind of a weird neighbourhood. Typical universe regions are busier, denser, more cosmopolitan, while our own is, well, suburban. It's the intergalactic equivalent of a sleepy cul-de-sac, plenty of space, no traffic, decent cosmic microwave background reception, but not many neighbours. You picture the Milky Way and Andromeda galaxies, the twin anchors of our local group, surrounded by about 50 smaller satellites. Together, they float along the edge of the local void, like boats tethered to a pier that overlooks an endless black ocean. And here's the twist. Because there's so little mass behind us, the gravity from denser regions beyond pulls harder, nudging our entire local group away from the void at a gentle drift of hundreds of kilometers per second. In other words, the void isn't just emptiness, it's a push. a negative presence sculpting motion. Scientists compare it to the way a soap bubble pushes its neighbours in a foam. Each bubble expands slightly, jostling others, until equilibrium forms. The universe behaves in a similar way, with voids and clusters balancing the cosmic fabric. The Milky Way's position, then, isn't random. It's part of a vast dynamic between presence and absence. You could almost call it cosmic feng shui, matter and nothingness arranging themselves in elegant symmetry. Now, here's your first quirky tidbit. Some early cosmologists jokingly suggested that the local void might actually be responsible for certain anomalies in cosmic expansion data, like a mischievous roommate hiding your keys and pretending they never existed. If we live in a region of lower density, light from distant galaxies would seem to stretch faster, fooling us into thinking the entire universe is expanding more quickly than it is. That idea never quite died. It hovers in scientific papers like a ghost at the edge of consensus. The implications are oddly personal. When you look up at the night sky and measure redshifts, you're not just seeing distant galaxies, you're also seeing how your local environment warps perception. Every observation carries the fingerprint of the void you live in. It's like doing astronomy through a funhouse mirror. The reflections are true, but they bend in subtle ways. You imagine standing on a quiet hillside, telescope cooling under a blanket of air so still it hums. The photons pouring into your lens left their galaxies millions or billions of years ago. They've crossed filaments, clusters, and finally this hollow domain of ours. Each one carries the faintest trace of that journey, slightly less scattering, slightly more stretch, a whisper of the emptiness it traversed. You are quite literally observing the universe from inside a bubble. If that makes you feel isolated, you're in good company. Even professionals describe the local void with a kind of melancholy reverence. One astronomer compared it to living at the edge of a cliff, staring into the dark sea of nothing. Another quipped that it's the best real estate for introverted galaxies, low noise, wide open views, very few cosmic neighbours borrowing sugar. Yet despite the humour, there's real mystery here. The local void's boundaries aren't sharply defined. They fade gradually into surrounding filaments, making it hard to tell where the nothing ends and the something begins. Different surveys measure its volume differently, and the debate over its true size remains lively. Historians still argue whether it's a single vast cavity or a cluster of overlapping smaller voids merging like bubbles in champagne. Either way, it's clear that our galaxy sits close to a cosmic divide, a border between density and desolation. And that's where the problem comes in. If your neighbourhood is unusually empty, then the universe might look different from where you stand than it does from elsewhere. Cosmologists build models assuming uniformity, that the universe looks roughly the same in every direction and at every location. But if we're inside a large underdensity, some of those models may wobble. It's the cosmic equivalent of trying to judge the weather while standing in a deep valley. You might think the sky is clear because the mountains block the storm. You take a slow breath, letting that idea settle. Emptiness isn't just absence, it's geometry. It shapes the flow of time, the bending of light, the illusion of distance. The local void is not a hole you could fall into. It's a gentle thinning of existence itself, a place where fewer galaxies formed, where the tug of gravity whispers instead of shouts. And somehow, against that backdrop, life has bloomed on a small blue world clinging to the edge of that nothingness. As your eyelids grow heavier, the cosmic scene softens. You picture the Milky Way suspended like a lantern over a vast well of darkness, its spiral arms glimmering faintly, its stars murmuring across the eons. The void below stretches endless, serene, and almost comforting. You're part of it, both fragile and essential, a speck of awareness flickering in the hollow between galaxies. You smile to yourself. It turns out living inside a huge void isn't so bad. It's quiet, the rent's cheap, and the view, well, unbeatable. You drift further outward now, away from the hazy rim of the Milky Way, where starlight grows faint and the black between galaxies thickens into true night. The human eye isn't built for this kind of seeing. Even your imagination squints. But that's okay, you have help. Astronomers have been mapping the invisible for decades, piecing together the universe's grand architecture like detectives reconstructing a crime scene, where almost all the evidence is missing. You begin to picture their tools, telescopes tuned not just to visible light but to radio waves, infrared glow, ultraviolet flashes, and X-ray ghosts. Each frequency reveals a new layer of cosmic structure. The great trick is that galaxies don't just sit somewhere, they move. Their light stretched as space itself expands. That stretching, known as redshift, is the cosmic barcode for distance. By measuring how much a galaxy's light has elongated, scientists can infer how far away it lies. Stack thousands of such measurements, and you begin to see patterns. In the 1970s, the first redshift surveys looked almost comically primitive, dots on paper representing galaxies painstakingly plotted by hand. But even those early sketches showed a revelation. Galaxies weren't sprinkled randomly. They clustered in long, thin tendrils, leaving enormous gaps between them. One researcher compared the pattern to a sponge soaked in stars. That phrase stuck because it felt right. Matter distributed not as an even fog, but as a lacy network of filaments and voids. The modern successor to those early maps is the Sloan Digital Sky Survey, or SDSS, a robotic telescope in New Mexico that's been scanning the sky since 2000. It's measured over 3 million galaxies, turning the once mysterious voids into identifiable structures. When the data are plotted in 3D, you can rotate the universe like a glowing coral reef. Every glowing branch is a cluster or filament. Every dark bubble between them is a void. And somewhere near the outer edge of one of those black pockets, there we are, quietly orbiting our unremarkable sun, wondering what it means. You imagine scrolling through that 3D map on a screen the size of a football field. The Milky Way appears as a single dot, one among billions, yet its surroundings show a curious asymmetry. To one side lies the local sheet, a flattened collection of galaxies loosely bound together like coins in a sleeve. Beyond that, space thins dramatically. The local void yawns open, swallowing volume but containing almost no light. On the other side stretch denser regions, the Virgo cluster, the Hydra Centaurus supercluster, and beyond them, the immense Laniakea structure that forms the gravitational landscape of our entire neighbourhood. You sit almost exactly on the continental shelf between the crowded cosmic mainland and the abyssal plain of emptiness. The funny thing about mapping nothing is that you need something to define its boundaries. You can't point at a blank part of the sky and say, "There's a void." You have to see where galaxies stop, and that absence draws the outline. In a way, voids are shaped by the presence of others. They exist only because something else doesn't. Kind of poetic, really. Even cosmic nothingness needs company to make sense. Some of the earliest cartographers of the voids treated their maps with the reverence of explorers. One famous image from 1986 shows the distribution of galaxies within 200 million light-years, a pattern so striking that journalists dubbed it the Stickman universe. Clusters appeared like knuckles connected by filaments of bone-thin galaxies, with vast black cavities in between. Historians still argue whether that visualization or its successor, the CFA2 Great Wall, first convinced scientists that the universe had a true large-scale structure rather than random scatter. What's not in dispute is how jaw-dropping it was. The cosmos had texture. Here's your quirky tidbit for the night. In the 1990s, one astronomer joked that if the universe really looked like a sponge, then cosmic cappuccino foam might be the most accurate earthly analogy. He wasn't entirely wrong. Modern simulations show that if you zoom out far enough, the cosmic web looks eerily like the bubbles on top of your morning latte, bright rims surrounding dark cavities, constantly evolving as expansion stretches the fabric. Somewhere, a barista of space-time must be proud. Now imagine tracing the invisible threads that form those filaments. They are made mostly of dark matter, the unseen glue that outweighs normal matter by roughly 5 to 1. It doesn't emit light, but its gravity guides everything that does. Gas collects along those filaments, condenses, ignites, and becomes galaxies. Between them, gravity's pull weakens, material drains away over billions of years, leaving behind the voids. You can almost feel the slow cosmic tide, mass flowing towards the filaments like rivers feeding oceans, emptiness expanding where the current departs. You wonder how scientists can possibly measure something that emits nothing. They use a mix of indirect tricks. Gravitational lensing, where light from distant galaxies bends slightly around invisible mass, acts like a topographic map of gravity itself. The peculiar motions of nearby galaxies reveal where the gravitational hills and valleys lie. And through enormous computer simulations, cosmologists recreate virtual universes, tweaking the balance of dark matter, dark energy, and ordinary gas until the resulting cosmic web looks like the one we observe. When it matches, they know they're close to the truth. Still, that truth is slippery. Every new survey redraws the borders. The local void might be 150 million light-years wide, or twice that, depending on how you define its density threshold. Its centre could be relatively spherical, or it might be more like a lopsided balloon squeezed by neighbouring filaments. Historians still argue whether we're truly inside it or merely on its boundary, the way someone living at sea level can still feel the pull of the mountains nearby. It's a strange paradox. The more precisely we map the universe, the more clearly we see how little of it we occupy. The visible matter, the stars, planets, gas and dust, amounts to less than 5% of the total cosmic inventory. The rest is invisible scaffolding. When you zoom out, the luminous parts form a thin frosting on an enormous gravitational cake. You, the Earth, everything you know, it's all icing. The real substance lies in what can't be seen. You pause for a moment, imagining that. The distances are so vast they lose meaning. But somehow the brain still tries to translate them. If the Milky Way were the size of a single grain of sugar, the nearest major cluster would lie hundreds of meters away, and the local void would be a balloon the size of a cathedral surrounding it. Between those scales, there's almost nothing. An aching emptiness that feels both hostile and serene. And yet mapping that emptiness has given us one of science's quietest joys: perspective. The same data that confirm our insignificance also confirm our connection. Every filament that stretches through the cosmic web began as a quantum ripple in the infant universe, a tiny imbalance in density that gravity amplified over billions of years. Those same ripples seeded galaxies, stars, planets, and eventually minds capable of looking back at them. In a literal sense, the universe is still writing itself, and we've just learned how to read the map. You can almost hear the hum of those distant measurements, radio dishes scanning, spectrographs clicking, computers rendering 3D plots of existence. Each pixel of data says, this is where light has been, this is where matter gathers, this is where nothing reigns. And all those pieces together whisper a bigger message, that the universe is not chaos but choreography, its structure intricate enough to inspire and humble in equal measure. Before the night fully takes you, you let one thought linger. Perhaps it's fitting that our species, so obsessed with mapping every inch of our own planet, has spent the last century charting a cosmos that resists every attempt to be pinned down. We are explorers of absence, cartographers of voids, and somewhere in those maps, in the thinnest region of the cosmic sponge, we've drawn a small label. You are here. You're still drifting through the mental hologram of the universe, watching it pulse and shimmer like a living organism. The farther you zoom out, the clearer its skeleton becomes. A sprawling network of cosmic filaments twisting through dark space, connecting clusters and superclusters in a lattice so delicate it looks almost organic. You can trace it with your finger, bright threads of galaxies weaving across invisible fields of gravity, forming junction like synapses in a brain. The spaces between those filaments, the yawning black hollows, are the voids. This is the cosmic web, and you are suspended within one of its thinnest strands. From your vantage point, the universe resembles something familiar yet alien, a honeycomb, a sponge, a tangle of silk. The metaphor shifts with every new map scientists make, but the underlying truth remains. Matter isn't scattered evenly. Instead, it's arranged in an intricate geometry that emerged from tiny ripples in the early universe's density field. Imperceptible variations that gravity slowly exaggerated over billions of years. What began as whispers in the infant cosmos now span hundreds of millions of light years. You picture the cosmic microwave background, that faint afterglow from 380,000 years after the Big Bang. It's a snapshot of the universe's first visible surface, a baby picture taken when atoms first cooled enough for light to travel freely. Within that glowing pattern, there are minute differences in temperature. Some regions a little denser, some a little emptier. Those slight variations, 1 part in 100,000, became the seeds of everything. The denser pockets eventually formed the filaments and clusters we see now. The less dense ones grew into the great voids that thread the darkness. Gravity, ever patient, sculpted the web from chaos. It's astonishing how well the idea fits reality. When supercomputers run simulations using only the known laws of physics, dark matter, dark energy, and gravity, they naturally produce this web-like structure. The resemblance between simulated universes and real galaxy maps is uncanny. Historians still argue whether it was the Millennium simulation of 2005 or the Illustris project of 2014 that first convinced skeptics that our cosmic web model was truly accurate. Either way, the conclusion was clear. This is not coincidence. The universe itself grows in patterns. Of course, being human, you can't help comparing it to things you know. Some call it the neural universe because it looks like a brain. Clusters as neurons, filaments as axons, voids as the spaces between. There's even a fringe study that claimed the statistical distribution of matter in the cosmic web mirrors that of neurons in a human cortex. The data are loose, the analogy poetic rather than scientific, but it's irresistible. You imagine consciousness itself as a small echo of cosmic structure, as though the universe practices the same architecture on every scale. Somewhere, perhaps, it's thinking in galaxies. Still, there's humour even in such grandeur. One astrophysicist once described the web as a universe-sized plate of spaghetti, which, to be fair, isn't far off. Filaments can stretch hundreds of millions of light years, but remain astonishingly thin, some less than 1% of their length across. Within them, galaxies cluster like pepper flakes in a source of dark matter and gas. Between the strands, the voids balloon outward, bubbles of underdensity growing as the universe expands. Each void gently pushes on its neighbours, inflating the cosmic web like yeast rising in dough. Here's the quirky tidbit of this section. In 2019, a team of scientists generated sound waves from the cosmic web, not literal noise of course, but mathematical translations of its structure into audible frequencies. The result? A low, eerie hum, somewhere between whale song and thunder slowed to a crawl. They called it the music of large-scale structure. It turns out that even emptiness can sing, if you know how to listen. As you glide along one filament, galaxies slide past like streetlights on an intergalactic highway. Some burn bright and blue, newborns spinning fast. Others glow with the tired red hue of ancient stars. These galaxies are the knots where filaments intersect, drawn together by gravity and the slow flow of matter. In those intersections, clusters and superclusters, the density is so high that hot plasma fills the spaces between galaxies, shining in X-rays. If you could see in that wavelength, the universe would look like a glowing nervous system, energy arcing along invisible lines. The cosmic web doesn't sit still either. Its filaments feed clusters with streams of gas, fueling star formation. Galaxies migrate along the threads, tugged by the gravity of denser nodes. Over billions of years, the voids between filaments grow larger, draining material like lowland sands losing water. Our local void, the hollow you inhabit by cosmic accident, is one of these expanding basins. Every second it becomes slightly emptier, while the web's bright filaments tighten their grip elsewhere. You could say the universe is slowly exaggerating its own structure, turning contrast up over cosmic time. You pause and let the scale sink in. Between one filament and the next, you could fit dozens of Milky Ways end to end and still have room for silence. That's how large the cosmic cells are. The average void spans about 100 million light years, though some, like the Bote's void, are nearly 10 times that. Historians still argue whether these immense spaces are truly empty or merely faintly populated with ghost galaxies, tiny, dim dwarfs that escaped detection until recently. Either way, the pattern remains. Filaments trace matter's skeleton, voids trace the universe's lungs. One breathes, the other exhales. It's tempting to think of this pattern as static, frozen in eternity. But the cosmic web is alive, at least in a slow geological sense. Gravity is still at work. Filaments merge, clusters collide, voids inflate. Over the next few tens of billions of years, the dark energy driving cosmic expansion will stretch the web further. Filaments will thin, galaxies will drift apart, and the great connectedness of today's universe will fade. Future observers, if any remain, might see only their local cluster. No web, no neighbouring filaments, just darkness. The grand network we marvel at now is a temporary flare of structure before isolation sets in. You smile at the cosmic irony. Humanity has emerged during a golden window, when the web is bright enough to map but not yet dissolved. We are cosmic archaeologists living mid-symphony, hearing enough notes to guess the melody before silence returns. The philosophers of future eons might never suspect that their universe was once threaded like lace. And yet, here we are, conscious and curious, drawing diagrams of a structure that dwarfs us beyond comprehension. You can almost sense the pulse of gravity through it all, the same invisible hand that pulled dust into planets, stars into galaxies, and galaxies into filaments. It's the same force that keeps your feet on Earth's ground, just scaled to unimaginable size. The thought makes you laugh softly. Every time you drop your keys, you're reenacting the motion of the cosmic web. You drift a little longer, letting the mental image dissolve into darkness. Filaments fade, galaxies dim, the cosmic symphony quiets. What remains is the underlying truth you are a thread in a much larger tapestry, woven by forces that care nothing for you and yet made your existence possible. The web that holds galaxies also holds atoms, minds, and dreams. And somewhere, within one of its thinner strands, you're awake, listening, mapping the invisible from the inside of a void. You're still gliding through that immense mental scaffold of galaxies when a question forms. How did we even find out that we live inside a void? It sounds like something a poet might invent after a long night staring at the sky. But this discovery has fingerprints, data, names, and even a few rivalries attached to it. The story begins decades ago, when astronomers first realized the universe was not the polite, uniform spread they expected, but a place of shocking unevenness. You imagine yourself stepping back into the late 1970s, bell-bottoms, analog calculators, and film-based telescopes. Redshift data were trickling in from observatories that measured galaxy velocities by hand, reading squiggly spectra like old fortune tellers reading palms. These astronomers, armed with little more than patience and caffeine, started noticing something strange. Whole swathes of the sky where there should have been galaxies appeared almost blank. At first, they blamed the instruments. Maybe the telescopes weren't sensitive enough. Maybe dust was hiding distant light. But as the data grew, the pattern held. By 1981, the first hints of true emptiness appeared in what became the Center for Astrophysics, CFA Redshift Survey, one of the earliest systematic attempts to map galaxies in 3 dimensions. When the data were plotted, the result looked like fireworks frozen mid-explosion, dense shells and arcs of galaxies surrounding enormous gaps. One of those gaps, roughly 250 million light-years across, was later dubbed the Boötes Void, a cosmic hole so enormous that it contained fewer galaxies than you could count on 2 hands. That discovery changed everything. If one void existed, surely others did. And if they surrounded us, then perhaps we were part of that structure too. The CFA survey's findings were both thrilling and uncomfortable. Cosmologists had long assumed that, on the larger scales, matter evened out, that if you zoomed out far enough, the universe would look smooth. These voids shattered that assumption. The universe had texture. It wasn't soup, it was foam. Fast forward a few years, and the focus shifts closer to home. Observers measuring the motion of nearby galaxies noticed that our local group, the Milky Way, Andromeda, and their small companions, seemed to drift at hundreds of kilometers per second relative to the cosmic microwave background, the universe's faint afterglow. The motion wasn't random. It seemed directed away from one region of the sky and toward another, as though something behind us were pushing, or more accurately, not pulling. That something was the local void. In 1987, astronomers Brent Tully and Richard Fisher published work suggesting that the region surrounding our galaxy was unusually underdense. The idea gained traction through the 1990s, as larger redshift surveys confirmed that, indeed, we live near the edge of a low-density bubble. Historians still argue whether Tully's data or later reconstructions from the 2-micron all-sky survey, 2MASS, deserve credit for naming the void, but no one disputes the general picture. The Milky Way sits like a bead on the boundary of emptiness. You picture those early cosmologists hunched over data printouts, coffee-stained and smudged with pencil marks. Each dot represented a galaxy, a smudge of light so faint it could vanish behind a thumb. Connecting them, they began to notice shapes, walls, filaments, and the enormous hollows between. It must have felt like walking into a dark room and slowly realizing that the walls aren't solid but made of spiderwebs. And then there was the problem of defining a void. How empty does something need to be to earn the title? Some researchers argued that anything less than 10% of the average cosmic density counted. Others set the threshold much lower. There were even debates over whether a region could truly be empty at all, given that dark matter might still thread through it unseen. The arguments grew heated. One physicist famously quipped, "A void is whatever my colleague calls my data." You can almost hear the laughter echoing across a conference hall. By the early 2000s, new technology made it possible to map the local universe in extraordinary detail. The Hubble Space Telescope provided high-resolution images, while ground-based surveys like Sloan and TUMAS filled in the gaps. A 2008 study using peculiar velocity measurements, the subtle deviations in galaxy motion from pure expansion, revealed something haunting. Galaxies at the edge of the local void were moving away from it faster than cosmic expansion alone could explain. It was as if the void were pushing them, not through any real force, but through the gravitational imbalance caused by its own emptiness. Here's your quirky tidbit. When scientists simulated that motion, they found that our local group behaves almost as if it's sliding down the side of a giant cosmic bowl, drawn toward denser regions while the void expands behind. One researcher jokingly called it the universe's slowest avalanche. You can't help but imagine our entire galaxy surfing on an invisible slope of gravity, coasting toward brighter, busier parts of the cosmos. The realization that we live near a void didn't just alter maps, it rippled through cosmology itself. Some theorists proposed that local underdensity could subtly distort our measurements of the Hubble constant, the value that describes the universe's rate of expansion. If we're inside a less dense region, space might appear to expand faster from our vantage point than it does elsewhere. That raised an unsettling possibility. Maybe part of the ongoing Hubble tension, the mismatch between different measurements of cosmic expansion, comes from the fact that we're judging the cosmos from an oddly privileged seat. Historians still argue whether that explanation holds any water. Most cosmologists think the local void is too small to significantly affect universal expansion rates. Others, however, aren't so sure. Papers continue to appear with careful titles like, "Could local underdensities explain apparent cosmic acceleration?" A polite way of saying, maybe the universe looks weird because we're sitting in the wrong neighborhood. You can't help smiling at the irony. Humanity once thought itself the center of all things. Then science humbled us, showing we're orbiting an average star in an average arm of an average galaxy. Now it turns out our position may not be so average after all. We're perched on the edge of one of the largest known underdense regions, the cosmic suburbs. A quiet place, sure, but with views unmatched anywhere else. If you listen closely, you can almost hear the hum of data centers processing terabytes of sky maps, turning random specks of light into coherent structure. The Milky Way's location isn't an accident on those screens, it's a landmark, the bright lip of a vast hollow. The local void isn't empty of meaning, it's a reminder that even nothingness has geography. You picture yourself standing on the balcony of the Milky Way, looking outward into that emptiness. There's no horizon, no sound, no wind, only the faint tug of gravity from the clusters beyond. Behind you lies the void, an expanding silence that has been deepening since the dawn of time. Ahead lies the crowded cosmos, dense with light and motion. You stand right between them, a witness to the contrast, watching the universe breathe. The funny thing is, in all this cosmic cartography, there's a touch of human vanity. We map the heavens as if we could ever step beyond them, as if plotting the void somehow makes it less terrifying. But perhaps that's the point. To measure nothingness is to claim a little mastery over it, to turn the vast unknown into a story you can tell yourself at night. And what a story it is, the tale of a species that looked into the darkness and said, "We live here." You hang suspended at the threshold of the local void, where the cosmic density thins like fog before sunrise. Out here, galaxies become rare, faint, solitary lanterns in an almost perfect dark. You turn slowly and face the way home, toward the local group, your small patch of galactic suburbia. It doesn't look like much, two spiral giants, the Milky Way and Andromeda, surrounded by a cloud of dwarf companions, maybe 50 or so in total. Together, they drift through space like a loose flotilla of lights, gravitationally bound yet adrift in the cosmic sea. This is your neighborhood, quiet, spacious, and by universal standards a little lonely. The local group spans about 10 million light-years, but most of that is just empty space. The distance between the Milky Way and Andromeda alone is around 2.5 million light-years, so far that if you sent a text message today, it'd arrive just in time to tell them we've evolved into something else. In another 4 billion years, those two spirals will merge in a slow, glowing collision. For now, they circle each other, like polite neighbours sharing a long driveway, exchanging the occasional gravitational wave instead of small talk. As you drift through this reunion in your imagination, you realise just how sparse it really is. In denser clusters, galaxies crowd together by the thousands. Separated by mere hundreds of thousands of light years, cosmic shoulder-to-shoulder traffic. But here, you could travel for eons before bumping into another major system. It's peaceful, yes, but there's a quiet melancholy too, as if you've wandered into a sleepy cul-de-sac on the edge of a vast city that forgot to expand this far. One of the brightest landmarks nearby is the Triangulum Galaxy, a smaller spiral that orbits both the Milky Way and Andromeda in a loose triangle. Beyond that, you see the dwarfs, the Magellanic Clouds, NGC 6822, Leo Fornax, and dozens of faint others, each so dim you could mistake them for smudges on the telescope lens. Many of these satellites are irregular in shape, their stars scattered like dandelion seeds, victims of gravitational harassment from their larger neighbours. It's a cosmic version of apartment living. The big galaxies dominate the property, and the little ones keep getting tugged around. Here's the historical anchor of this part. Back in 1924, Edwin Hubble used observations of the Andromeda Galaxy to prove that it lay far outside the Milky Way, settling a heated debate about the universe's scale. Before that, many astronomers thought the Milky Way was the entire universe. Hubble's discovery didn't just open the sky, it expanded human perspective beyond anything imaginable. Historians still argue whether that realization, or the later discovery of cosmic expansion, had the bigger philosophical impact, but both made the same point. We are small participants in a vast dynamic cosmos. The local group sits on the rim of the local void like a cluster of lights along a cliff edge. To one side, the gravitational landscape slopes downward into the void's emptiness. To the other, it rises toward the dense structures of the Virgo cluster and the Laniakea supercluster beyond. This imbalance creates a subtle motion. The entire local group drifts at about 100 km per second relative to the cosmic microwave background, as though being gently pulled toward the mass ahead while the vacuum behind releases its grip. You imagine the sensation, if galaxies could feel it, as a long, slow sigh. The local group is literally sliding away from emptiness. It's a strange kind of gravity ballet. The void doesn't pull, it releases, and in doing so, it shapes everything. The Milky Way, in its lazy spiral, responds like a feather caught in a planetary scale exhale. You are, without realizing it, part of that motion carried through space by forces too vast to name. Your quirky tidbit for tonight: astronomers once described the local void as a ghost neighbour who never visits. That phrase appeared in a 2007 conference when researchers were joking about how difficult it is to measure something defined by its absence. The audience laughed, but the metaphor stuck. The local void really is like a ghost, unseen, intangible, yet undeniably influential. Its very lack of matter shapes how galaxies move and how we measure cosmic expansion. Now, if you zoom in closer, the local group's serenity begins to look a bit deceptive. Each galaxy is busy, seething with stellar births and deaths. In the Milky Way's core, stars orbit a supermassive black hole weighing 4 million suns, or spiral arms churn with nebulae, nurseries of glowing hydrogen where stars ignite like fireflies in slow motion. The Andromeda Galaxy mirrors this activity, only on a slightly grander scale. Even amid cosmic quiet, there's motion everywhere. Yet compared to the bustling clusters of the Virgo region, we're living in cosmic countryside. The average density of galaxies here is less than 1/10 of that in rich clusters. There's no searing X-ray gas filling the space between galaxies, no violent interactions every few million years. It's the galactic equivalent of living in a small town where the loudest event is a passing meteor shower. Astronomers often call it a low-density environment, but it might as well be called a peaceful retirement zone for galaxies. Historians still argue whether this isolation affects the Milky Way's evolution. Some think our quiet surroundings allowed a stable environment for life to develop, a sort of cosmic safety zone, far from the radiation storms of crowded clusters. Others point out that even in emptier regions, cataclysms happen on smaller scales. Supernovae, gamma-ray bursts, rogue comets. Maybe we were just lucky enough to exist during one of the calmer chapters. Either way, our address on the edge of a void might have made Earth's story possible. As you picture this, a kind of cosmic homesickness sets in. It's not sadness exactly, but awe tinged with awareness. Every star you've ever seen, every satri, every sound, all of it unfolds in this quiet galactic backwater. We gaze out at the universe from a calm corner, and from that perspective, the wildest cosmic drama seems almost serene. You think of the void again, an expanding nothing that cradles everything we know. The paradox is beautiful, life emerging not despite emptiness, but because of it. Your eyelids grow heavy as the scene fades. You see the local group's scattered lights drifting against the velvet backdrop, faint threads of starlight tying them together. The Milky Way hums softly, a glowing spiral edge lit by billions of suns. Beyond its arms, silence reigns. You take one last look into the void, your cosmic neighbour, your ghost companion, and feel a strange comfort. After all, every home needs a bit of space, or you float now on the invisible slope of gravity, that quiet, tireless force that holds the entire cosmic web together and whispers across unimaginable distances. From your vantage point near the edge of the local void, you can almost feel it, not as a tug or a pull, but as a faint pressure on your imagination. Suggestion that somewhere beyond the nothing, something heavier is calling. Galaxies, clusters, and superclusters are all part of that call, and your own galaxy, the Milky Way, answers it constantly, drifting through space like a leaf in a slow, invisible current. Gravity doesn't roar or flash, it hums. It's the background music of existence, and in this region of space where the local void meets the denser walls of the cosmic web, that hum is complex. Every nearby cluster, every thread of dark matter adds its own note to the song. Astronomers call this grand symphony of motion the cosmic flow, and our local group is one of its quieter instruments. The flow isn't random. The galaxies around you are moving away from the local void, drawn toward regions of higher density. The Virgo cluster, about 50 million light-years away, tugs at us with the mass of thousands of Milky Ways. Beyond it, the Hydra Centaurus supercluster and the mysterious Great Attractor add their own pull. Combined, these forces send our galaxy, and everything in it, drifting through the universe at roughly 600 kilometers per second. You might not feel it, but at that speed, you cover the distance to the moon in about 12 minutes. For decades, astronomers tried to measure this motion precisely, using the subtle imprint it leaves on the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. When they compared the CMB in different directions, they found it wasn't perfectly uniform. One side of the sky was slightly warmer, the other cooler, by a few thousandths of a degree. That difference, called the dipole anisotropy, revealed our movement through the cosmos. The warm direction is the one we're heading toward, the cool direction, the one we're leaving behind. And guess what's behind us? The local void. It's tempting to think of the void as a physical thing pushing us, like a great cosmic wind at our backs, but that's not quite how it works. It's the absence of mass that matters. Gravity is a one-way conversation, only presence speaks. Where there's less matter, there's less gravitational pull. So when the local void expands, the galaxies on its rim, including ours, naturally fall away from it toward denser territory. It's a bit like standing between two magnets, one strong and one weak. You don't need the weak one to push you, the strong one simply wins. Here's your quirky tidbit. A 2014 study nicknamed this drift the cosmic shove, which sounds like something a mischievous deity might do when bored. Give our galaxy a tiny nudge just to see what happens. The name stuck for a while because honestly, who doesn't enjoy the idea of the Milky Way being gently bullied across the universe? Later, scientists refined the term into void-induced flow, which, while more accurate, is much less fun to say. The local void's gravitational whisper creates measurable consequences. It helps define the direction of our motion relative to nearby structures, but it also complicates the way we interpret cosmic expansion. Imagine trying to measure how fast the universe stretches while standing on a moving walkway. You'd have to account for your own drift. Similarly, that's our galaxy's peculiar velocity. Its deviation from the average cosmic expansion must be subtracted from every large-scale measurement we make. Get it wrong, and the whole picture tilts. Historians still argue whether the local void's gravitational influence was underestimated in earlier cosmological models. Some claim that ignoring its role led to subtle errors in distance estimates for nearby galaxies. Others think its effects are too minor to worry about. But either way, the debate continues, because every new measurement reveals just how much motion defines the cosmos. Even stillness, it seems, is an illusion created by balance forces. You imagine what it would be like to see those forces directly, to watch the gravitational field like ripples in water, spreading and colliding, forming troughs and peaks. That's essentially what the universe is doing all the time, flowing toward balance but never quite reaching it. Each cluster tugs on another, each void expands in response. It's less a stable structure than a perpetual negotiation between attraction and absence. Gravity also carries memory. Every motion today reflects billions of years of past interactions, collisions, mergers, expansions, evacuations. The Milky Way's current drift is the sum of countless gravitational handshakes stretching back to the dawn of time. To track them all would be like tracing every swirl in a cup of coffee back to the exact way you stirred it. And yet, that's what astronomers try to do. They reconstruct the cosmic flow field, mapping invisible gravitational tides across hundreds of millions of light years. You think about how delicate that task is. Even tiny measurement errors, fractions of a percent, can flip conclusions. The void might seem deeper or shallower depending on how distances are calibrated. The Virgo cluster might appear closer or farther, depending on how you correct for redshift distortions. It's cosmic detective work at its finest, and gravity is the chief suspect. Invisible, omnipresent, guilty of everything but impossible to see. Still, the most haunting realization comes when you realize this motion isn't temporary. The local void will keep expanding, and as it does, it will continue to influence us. Our local group, caught between emptiness and abundance, will keep sliding toward the denser regions of Laniakea. Over billions of years, this drift will subtly reshape the cosmic geography. The void will grow larger, the filaments thinner, and our once crowded corner of the universe will stretch into deeper solitude. And here's the quiet punchline. Gravity's whisper never stops. It's speaking to you right now, holding your feet to the floor, keeping the moon in orbit, balancing the Milky Way's arms, steering entire clusters across space. You live inside its song. It's so constant you forget it's there, the same way fish forget the ocean. But step far enough into the cosmic void, and you feel its rhythm again, an inaudible bass note thrumming through reality, a pulse older than light itself. You close your eyes and let that thought settle. Somewhere beyond the darkness, the great attractor hums. Behind you, the local void deepens. Between them, your galaxy glides, perfectly balanced between presence and absence. The universe moves in silence, but you can almost hear it if you stay very still. You drift with that cosmic current a little longer, feeling the vastness of motion that carries you in everything you've ever known. But as your thoughts expand with it, something unsettling slips in. What if all this emptiness isn't just shaping our motion, but also our measurements? The farther we look into space, the faster distant galaxies seem to flee from us. That observation, first made by Edwin Hubble in the 1920s and refined for nearly a century, gave us the concept of an expanding universe. And yet, there's a modern complication. The rate of that expansion, called the Hubble constant, doesn't agree when measured in different ways. The numbers don't line up. It's one of cosmology's great headaches, and one possible culprit lurks right here in the quiet vacuum of the local void. The question goes like this. If we live in an unusually empty region, could that trick us into thinking the universe is expanding faster than it really is? Light from distant galaxies passes through a variety of cosmic environments on its way to our telescopes. If we're sitting in a relatively underdense bubble, that light will enter our neighborhood already stretched by expansion. But because there's less mass around us to slow the stretching, the effect we see may appear exaggerated. To a casual observer, it would look like distant galaxies are running away faster than the equations predict. It's a cosmic optical illusion caused by geography. This idea, the so-called void bias, has been tossed around for decades. Some researchers think it could partly explain the stubborn mismatch between the Hubble constant measured from the early universe, using the cosmic microwave background, and the value measured from nearby galaxies and supernovae. Historians still argue whether the first serious version of this argument came from the Swiss astrophysicist Georges Lemaitre in the 1930s, who speculated about inhomogeneous expansion, or from modern cosmologists in the early 2000s, revisiting the same intuition with computers instead of chalkboards. Either way, the suspicion that our local environment might distort cosmic data has never fully gone away. You imagine the universe as a rising loaf of bread, each galaxy a raisin being carried outward by the swelling dough. In that image, the expansion looks uniform. Each raisin sees all the others moving away. But if a section of dough had fewer raisins, less mass, it would rise a little faster. That's us, the under-raisined neighbourhood. Our little patch of dough inflates slightly quicker, giving the impression that the entire loaf is speeding up. When astronomers discovered in the late 90s that the universe's expansion really is accelerating, they blamed a mysterious repulsive force called dark energy. But what if, at least in part, that acceleration is just what it looks like from inside a faster rising bubble? The void hypothesis doesn't eliminate dark energy entirely, but it teases it like a skeptical friend at a dinner party. It asks, "Are you sure the table's level?" and then watches as everyone remeasures with embarrassed frowns. In fact, some early papers argued that living inside a large underdensity could mimic the observational signatures of dark energy so well that we might have misread the universe's true geometry. Later studies toned down that optimism. Simulations showed the effect was too small to explain all the acceleration. But the conversation never fully died. Here's your quirky tidbit. One physicist jokingly named this idea the cosmic valley mirage, comparing it to the way sound echoes differently in a mountain hollow. If you shout from inside a bowl, the returning echoes trick your ears about distance and speed. Likewise, cosmic light echoing through a gravitational hollow might trick our telescopes. It's the universe's oldest party trick, performed at scales too vast for applause. To test the illusion, astronomers measure how galaxies cluster across immense distances. In a perfectly uniform cosmos, the clustering strength should be the same everywhere once you account for cosmic time. But if you find that nearby galaxies seem less tightly packed than the average, that's a clue that you live in a local underdensity. Those surveys, 2MASS, Sloan, and more recently DESI, the dark energy spectroscopic instrument, suggest that the Milky Way's neighbourhood is indeed slightly emptier than average, though probably not enough to fake the entire acceleration. Still, even a few % difference matters when your measuring stick is the universe itself. Historians still argue whether this local underdensity might resolve the Hubble tension, the persistent disagreement between measurements from the early and late universe. One camp says yes, a void could inflate the locally measured value by several kilometers per second per megaparsec, exactly the gap we see. The other camp counters that the effect would be too small unless the void were improbably huge, extending hundreds of millions of light years farther than observations allow. The debate has become a quiet tug-of-war between data interpretation and cosmic humility. You imagine scientists hunched over graphs, arguing softly at conferences while coffee cups cool beside laptops. One leans in and says, "Maybe it's not new physics, maybe it's just our neighbourhood." Another replies, "Or maybe the universe really is stranger than we thought." Both smile because in truth, they're probably both right in some measure. The void doesn't cancel dark energy, just complicates how we perceive it. The cosmos, it seems, refuses to hand us simple answers. As your thoughts wander through those arguments, you realise how fragile perspective can be. A single assumption, like uniformity, shapes decades of theory. If that assumption cracks, so does everything built on top of it. It's humbling to think that our grand models of the cosmos depend on the accident of where we happen to live. If Earth had formed in a dense galaxy cluster instead, our measurements might tell a slightly different story. The constants we consider universal could shift subtly, like colours under different lighting. You picture yourself standing at the edge of the local void, flashlight in hand, trying to judge the speed of distant fireflies by how their light flickers through the mist. That's what astronomers are doing, just at a scale so large that even metaphors creak under the weight. The void behind you doesn't merely represent absence, it's part of the measuring stick itself, a silent collaborator in every equation. In the end, whether the local void significantly alters cosmic expansion or merely hums in the background, it reminds you of a deeper truth. The universe we see is filtered through where we stand. Space itself bends our perception, reshaping even our understanding of time and acceleration. The darkness outside your window tonight is not just emptiness, it's a lens, subtle and vast, through which you read the story of everything. You take a slow breath. Somewhere beyond that lens, galaxies continue to race outward, their light stretched thin, carrying the history of expansion within every wavelength. Perhaps dark energy drives them. Perhaps geometry tricks us. Either way, the void watches silently, its gravity, or lack thereof, folding truth into illusion. And you, perched at the edge of nothing, try to listen for what the universe is really saying. You're still floating in that hush of deep space, but now your attention drifts toward the light itself, the real messenger of cosmic truth, and sometimes its greatest liar. Every glimmer you see from the heavens is a story told across time, but light doesn't always tell the whole truth. It stretches, bends, and sometimes plays tricks depending on the landscape it travels through. And when that landscape includes something like the local void, where the fabric of space is slightly less crowded with matter, the story light tells can become a little distorted. Imagine a photon leaving a distant galaxy, young and eager, setting off on a journey of hundreds of millions of years. It passes through crowded filaments where galaxies cluster, where gravity pulls at it like thick syrup slowing its pace. Then it glides into a void, our void, and suddenly it moves through emptier space, like stepping into a vast desert where sound carries differently. Nothing stops it, but something subtle happens. The very expansion of space stretches its wavelength. When it finally reaches your telescope, the light is redder, longer, cooler. That change, called redshift, is the fundamental tool astronomers use to map the universe. But the catch is that the rate of redshift depends not just on cosmic expansion, but also on the journey light takes to get here. If you live near a void, your incoming light might be stretched a little more than usual. It's like listening to music through a hall that's slightly too large. The notes echo and you misjudge the tempo. For the universe, that means your distance estimates skew subtly upward. Distant galaxies seem farther, older, or faster moving than they really are. The effect is tiny but persistent, and when your laboratory is the entire cosmos, even tiny errors echo loudly. Astronomers try to correct for this by modelling how light propagates through different densities of matter. They account for gravitational lensing, the way mass bends light around it, and for the integrated Sachs-Wolf effect, where photons gain or lose a little energy as they climb out of gravitational wells or drift through expanding voids. Historians still argue whether this latter effect was first detected in the 90s, or not conclusively confirmed until a 2000 cross-correlation between the cosmic microwave background and galaxy surveys. Either way, it revealed something profound. Light isn't just a passive traveller. It reacts to the universe's shape along its path. You think of photons as tiny hikers crossing a mountain range of invisible gravity. Every hill and valley along the way adds or subtracts energy, changing how the light looks when it finally arrives. By the time it reaches you, that light carries not just the story of its source galaxy, but also the footprints of every void and cluster it passed through. And here's the weird part. Because our Milky Way sits right beside the local void, almost every beam of light we catch has to traverse that emptiness before we see it. The void is our cosmic filter, our silent editing room. Here's your quirky tidbit. Some astrophotographers, when joking about atmospheric distortion on Earth, call it local void interference. It's half a joke, half a jab at the fact that no matter how perfect your optics are, the biggest distortions often come from the large-scale structure of the universe itself. Even the sharpest image is slightly warped by the cosmic terrain between here and there. The deeper the void, the more deceptive the clarity. There's an eerie poetry to this. The universe is constantly whispering, but you never quite hear its true voice. Every observation is a translation through space, filtered by gravity and expansion. When astronomers calibrate their instruments, they're not just adjusting for atmospheric turbulence or instrumental noise, they're correcting for reality itself, bending under its own weight. You picture yourself sitting beside a large telescope, maybe in Chile or Hawaii, the night air thin and electric. The detector glows faintly red as it captures photons that began their journey when dinosaurs still walked the Earth. Those photons have passed through the densest clusters, the darkest voids, perhaps even through intergalactic dust fields. Each one has been pulled, squeezed, and cooled like a traveller aged by their long voyage. When they finally fall onto your mirror, they bring with them the imprint of the entire universe they crossed. You're not just seeing the source, you're seeing everything between. Light from nearby galaxies plays different games. Some of it scatters off hot gas, some reflects faintly from the intergalactic medium. The further it travels through emptiness, the less interference it encounters, which is why the void gives us such sharp but potentially deceptive views. Think of it as looking through the world's cleanest window, except the glass itself subtly changes shape as you stare. Historians still debate whether early measurements of distant supernovae, those famous 1998 results that implied cosmic acceleration, might have been affected by the line-of-sight variations through voids. The consensus today is that they weren't, at least not enough to explain away dark energy. But the question lingers, haunting the margins of astrophysical papers like an unresolved chord. Could the universe's greatest mystery partly be an artifact of how light lies when it crosses the emptiest spaces? In some sense, you've always known this intuitively. Look at a city's skyline through heat haze, and the buildings seem to ripple. Look through ocean water, and the seafloor dances. The medium between you and the view always shapes the image. In space, the medium is space-time itself, warped, stretched, sometimes thinner, sometimes thicker. Light doesn't move through it. Light is carried by it, and space-time, like any courier, occasionally smudges the message. You can almost hear the photons complaining after their journey. You try crossing 200 million light-years of fluctuating density and not look tired. You smile. It's hard to blame them. After all, we ask light to do impossible things, measure distance, reveal truth, and never exaggerate. But the truth is that the universe's emptiness is not neutral. The void bends honesty into subtle curves. As you float there, you watch beams of light thread the blackness, faint lines of colour vanishing into infinite distance. The emptiness amplifies them, makes them seem brighter, cleaner. It's beautiful, almost too beautiful, a reminder that clarity can deceive. The photons keep coming, bearing messages warped by their path, and you, perched on the boundary between nothing and everything, keep reading them, trying to separate truth from distortion. In the end, you realise that light, like life, tells its story imperfectly. It can only speak from its experience, and when its journey begins in the depths of the cosmos and ends inside your fragile earthbound eyes, maybe a little distortion is the price of wonder. You're still drifting in the dark, watching those weary photons ripple past when something catches your attention, a faint haze where the edge of the local void meets a tenuous fringe of galaxies. It isn't a sharp boundary, more a slow fade from emptiness into existence, like mist dissolving into cloud. Out there, the galaxies look different. Fewer stars, fewer clusters, some seem misshapen, pale, or half-formed. These are the galaxies on the edge, the inhabitants of the cosmic shoreline, where density finally begins to rise after hundreds of millions of light-years of nothing. You can think of them as the hermits of the universe, quiet, eccentric, and profoundly affected by the isolation in which they were born. In crowded regions like the Virgo or Coma clusters, galaxies live fast and die bright. Their stars ignite in furious bursts, burn through gas quickly, and then fade into red, exhausted husks. Collisions are common there, gravitational brawls that merge spirals into elliptical giants, scattering stars like sparks. But here, at the margin of the local void, the opposite is true. With almost no neighbouring galaxies to collide with and little external gas to draw in, these edge-dwellers evolve slowly, cautiously. Their disks are thin, their star-forming regions faint. They've lived entire cosmic lifetimes without the chaos of collision. One of the most studied of these loners is the galaxy NGC 6503, a modest spiral perched right at the rim of the local void. Discovered in the late 19th century but fully understood only with modern instruments, NGC 6503 sits about 18 million light-years away and appears almost perfectly edge-on from Earth. It's sometimes called the Lonely Galaxy, though that's probably unfair. It has a halo of faint companions, dim dwarves, that drift like crumbs around a larger loaf. Still, compared to galaxies and crowded clusters, NGC 6503 is a recluse. Its rotation curve, gas density, and subdued star formation make it a near-perfect example of how life in the void suburbs shapes evolution. You imagine approaching it in your mind, flying through the thinned-out starlight. There's no grand cluster glow, no overlapping halos of other galaxies, just the delicate blue edge of a spiral slicing the dark like a quiet comet. Inside, stars orbit undisturbed, their orbits nearly perfect circles. Without tidal forces tugging from outside, the galaxy keeps its symmetry like a well-balanced top. Yet that serenity has a cost. Star formation proceeds slowly, like embers reluctant to flare. In some regions, you can almost see the hunger, the interstellar medium depleted, thin as breath. Historians still argue whether the first identification of galaxies affected by the local void came from Brent Tully's velocity maps in the early 2000s, or from later refinements in the Cosmic Flows projects a decade later. Either way, what those maps revealed was striking. Galaxies at the void's rim tend to drift outward faster than the expansion of space alone would predict. The absence behind them acts like a silent shove. Each of these systems, including NGC 6503, is subtly escaping the void, sliding toward denser filaments beyond. You can almost feel the momentum, slow, unstoppable, geological in scale. Your quirky tidbit tonight. One astronomer once called NGC 6503 the introvert's galaxy, saying it lives in a cosmic version of the countryside with no neighbours to borrow milk from. The phrase made its way into a 2010 press release, and the nickname stuck in a few astronomy blogs. Somewhere out there, amid billions of roaring clusters, one little spiral got famous for being shy. When you look at that galaxy, though, it's hard not to feel a twinge of recognition. In a way, the Milky Way isn't so different. We too occupy the edge of an underdense region, part of a small quiet group instead of a bustling cluster. And like NGC 6503, we seem to benefit from that peace. Our galaxy's disk is orderly, our star formation steady but sustainable. Maybe the void gives certain galaxies room to breathe. If every neighbourhood were as crowded as Virgo, perhaps fragile things like life would struggle to arise at all. The physics behind this calm isolation is elegant. In dense clusters, gravitational tides pull gas from galaxies and strip them bare. Radiation from hot intercluster plasma can quench star formation entirely. But near void boundaries, those effects fade. Galaxies there retain more of their gas, their disks remain intact, and their halos extend further into the dark. Over billions of years, these differences accumulate, shaping entirely different evolutionary paths. If the universe were a forest, void-edge galaxies would be the slow-growing trees on the outskirts, gnarled but enduring. Astronomers have noticed another pattern. Galaxies in and around voids often spin faster, relative to their mass, than those in denser regions. The reason isn't fully clear. Some theories suggest that the weaker tidal forces of emptiness let them retain their angular momentum. Others point to early formation histories where fewer interactions preserved their pristine conditions. Historians still debate which mechanism dominates, and each new dataset nudges the argument in a slightly different direction. What everyone agrees on is that void galaxies are laboratories of cosmic minimalism, simple environments where gravity and isolation dance in near purity. You float along that boundary, gazing into the void behind and the faint galactic wall ahead. The emptiness glows faintly with the scattered light of distant structures, like a city's haze seen from the desert. You realise that the void isn't truly black, it's just shy. There's always a little something, even in nothing, a whisper of gas, a faint dwarf galaxy glowing with a few stubborn stars, the residue of cosmic history refusing to fade. If you could hear the galaxies on the edge, they'd probably sound content in their solitude. No constant harassment from neighbours, no gravitational bullying, just the slow hum of internal rotation and the occasional flare of a supernova to keep things interesting. You can almost imagine one of those galaxies looking back across the void toward us, thinking, over there, those bright ones are too loud. You smile. Maybe the universe, like people, needs both cities and countrysides, dense, chaotic clusters for drama and quiet outskirts for reflection. The local void provides the silence between the cosmic notes, the negative space that makes the pattern visible. Out here, the galaxies evolve in peace, glowing softly against the eternal dark. And you, poised at the edge of that silence, can almost hear them breathing. You linger at the edge of the local void, looking out toward the brighter, more crowded regions that pull at us with invisible hands. Beyond that gulf of emptiness lies something magnificent, an immense continental shelf of matter called Laniakea, the supercluster that encompasses our entire galactic neighbourhood. The name means immense heaven in Hawaiian, and it fits. Imagine a landscape so vast that it holds hundreds of thousands of galaxies, each one a city of stars, all connected by the faint filaments of the cosmic web. You, the Milky Way, Andromeda, and every nearby galaxy are drifting through this grand gravitational basin together, carried along by its pull like leaves swirling in a cosmic tide. Laniakea isn't a simple structure you can see through a telescope. It's an idea revealed through motion. Scientists discovered it in 2014 using precise measurements of galaxy velocities to trace how matter flows through space. Every galaxy moves not just because of cosmic expansion, but because of the combined gravity of all its neighbours. By mapping these motions, astronomers realised that the Milky Way and roughly 100,000 other galaxies share a common gravitational destination, an enormous attractor region more than 100 million light-years across. That shared destiny defines a supercluster, and for us, that supercluster is Laniakea. When you look at it on a map, it's breathtaking. Our local group sits on one of its outer filaments, right where the edge of the local void meets the basin of attraction. The cosmic geography feels strangely familiar. An oceanic void on one side, a sprawling continent of galaxies on the other, and us perched on the coast. The galaxies within Laniakea flow inward, down gentle gravitational slopes, toward a region known as the Great Attractor, a dense knot of mass hidden behind the Milky Way's disk. The pull is subtle but irresistible. Everything nearby, Virgo, Hydra, Centaurus, even us, slides slowly toward that unseen heart. Historians still argue whether the concept of Laniakea truly replaced older notions of superclusters or merely renamed them with the better data. In the 1980s, astronomers already spoke of the Virgo supercluster, which contained the local group and its neighbours. Laniakea simply revealed that Virgo was part of a much larger interconnected structure. It was as if someone had turned the lights up in a dim room and suddenly seen the rest of the furniture. The local void, ironically, helps define the boundaries of this cosmic continent. On one side, gravity wells funnel galaxies inward toward the Great Attractor. On the other, emptiness or pushes outward, expanding faster than the average universe. The balance between these two forces, pull from Laniakea, release from the void, determines our cosmic motion. It's an elegant tug of war, with our galaxy as the rope's midpoint. The local group is literally being drawn into one region while being freed from another. Motion through space isn't just travel, it's compromise. Your quirky tidbit tonight. When Laniakea was first named, the research team consulted Hawaiian language experts to capture the poetic vastness of the discovery. One linguist warned them that Lani could mean both sky and spiritual realm, while Akea meant immense or broad. The final translation, immense heaven, was chosen to honour the island where the discovery was analysed, but also to remind everyone that astronomy is, at its core, about reverence as much as math. Somewhere between data points and starlight, there's still a bit of mythology. You picture the supercluster's shape, not a perfect sphere, but a sprawling coral reef of filaments and nodes. The Virgo cluster glows at one end like a central reef hub, while smaller groupings, Hydra, Centaurus, Antlia, branch out in arcs and tendrils. If you could trace every galaxy's path, they'd form streaming lines, rivers of motion converging toward the gravitational basin in Centaurus. Our local group's stream runs along the border, like a tributary feeding into a larger ocean current. The metaphor isn't far from the truth. These motions are fluid, graceful, governed by gradients of mass and time. The Great Attractor itself remains partly mysterious. It isn't a single object, but a gravitational convergence zone, an accumulation of mass from several clusters overlapping in projection. Hidden behind the thick dust of the Milky Way's plane, it eluded direct observation for decades. In the mid-80s, its existence was inferred only from how nearby galaxies seemed to accelerate toward one region of the sky, as though drawn by a hidden hand. Some thought it might be an enormous unseen supercluster. Others speculated about exotic matter concentrations. Later surveys revealed that the Hydra-Centaurus cluster accounts for much of the attraction, with additional pull from an even larger region beyond, now known as the Shapley supercluster. Together they form a deep gravitational basin, the downhill slope of Laniakea's vast terrain. To visualize it, imagine space as a topographic map. The dense clusters are valleys, the voids are hills. The Milky Way sits high up on a ridge, the local void behind us like a steep incline pushing outward, and Laniakea stretching ahead like a descending plane. Over billions of years, galaxies will continue sliding downhill into that gravitational basin, even as cosmic expansion pulls everything apart. Gravity wins locally, expansion wins globally, and we ride the balance point between the two. You pause to take that in. Every sunrise, every orbit of Earth, every rotation of the Milky Way around its centre. Beneath all of it, An invisible drift continues, a slow glide toward the heart of Laniakea. It's so gentle that not even the most sensitive instruments can feel it directly, yet over eons, it defines our cosmic address as surely as latitude and longitude define your home on Earth. We are moving not just through space, but through a living geography of gravity. Historians still argue whether this interconnected view of the universe truly captures its essence, or merely flatters our love of structure. Some insist the term supercluster will fade as we refine our definitions, replaced by continuous flow regions instead of discrete chunks. Others defend it for its poetry. Even if the borders blur, we still need words that help us feel the grandeur of belonging to something larger. Laniakea, they say, reminds us that cosmic mapping is a kind of storytelling. As your thoughts drift, you look once more toward the local void. It's easy to forget, but without that emptiness behind us, the balance of motion would tilt. The void pushes as Laniakea pulls. We are poised in dynamic tension between absence and abundance. You realize that this, more than anything, defines your place in the universe, not a static coordinate, but a constant journey. The cosmos isn't still, it flows. Every star you see tonight is caught in that same slow river, all heading home together, wherever home means for galaxies. You hover for a while within that mental map of Laniakea, an immense heaven of clustered light, before zooming outward again, letting the scale expand until the supercluster looks like just another bubble in a vast frothy sea. The filaments connecting it to its neighbours stretch thin, and between those threads the dark hollows yawn wider. The universe, it turns out, is mostly nothing, a delicate foam of galaxies separated by enormous voids. Our local void is just one of millions, part of a structure so immense and intricate that even naming it feels like hubris. And yet, cosmologists keep trying, because what they see at this scale hints at something profound. The universe might be not just a web, but a foam of bubbles, each void expanding like the surface of a cosmic soap film pressed against others, forming a lattice of emptiness that fills all of space. It's a comforting and unsettling idea all at once, the bubble universe model. Not in the multiverse sense, though we'll get to that later, but in the literal structural sense. The cosmos behaves like a fluid. Where density is high, matter clumps. Where it's low, it drains away, leaving behind cavities that inflate with time. Imagine pouring milk into coffee and watching the foam form and separate, each bubble surrounded by thin, shining walls. That's the large-scale universe, only in 3 dimensions and moving at the speed of eternity. Historians still argue whether the bubble analogy first arose from the Great Redshift surveys of the 1980s, or from earlier theoretical work on gravitational instability in the 70s. Either way, the discovery that galaxies align along the borders of vast voids forever changed our understanding of structure formation. The cosmos wasn't homogeneous after all, it was cellular. The same physics that causes bubbles in a glass of soda could, in principle, describe the scaffolding of galaxies across billions of light years. When astronomers run computer simulations of the early universe, they start with nearly uniform gas sprinkled with tiny fluctuations in density, quantum wrinkles inflated to macroscopic size by the Big Bang's rapid early expansion. Over time, gravity amplifies those wrinkles. Matter collapses into sheets and filaments, leaving behind expanding gaps between them. The result, after 13.8 billion years, is the same pattern we see in surveys. Walls of light enclosing spherical regions of almost nothing. The resemblance to soap bubbles isn't poetic exaggeration, it's mathematical precision. The Voronoi tessellation often used to model void networks is literally the same geometry that describes bubble foam. Here's your quirky tidbit. In the 1990s, an astrophysicist with a flair for humour once demonstrated cosmic structure by blowing bubbles in a lecture hall, letting them float under a spotlight while he explained galaxy clustering. When one burst, he paused dramatically and said, "There goes a dwarf galaxy merger." The audience laughed, but the analogy stuck. Somewhere between playfulness and profundity lies the best way to teach the universe. Now, consider what this means for our own existence inside the local void. If every region of space is part of this great foam, then our galaxy's home bubble is just one in an endless mosaic. The boundaries between voids form the filaments where galaxies gather, much like the thin membranes between bubbles. Where several voids meet, the filaments thicken into clusters. In this model, the local void isn't isolated, It's connected to a larger network of underdensities that extend hundreds of millions of light years. The cosmic web, at its grandest scale, is the pattern left by these expanding hollows. There's something elegant in that symmetry. Emptiness creates structure. Absence defines presence. Without voids pushing outward, the filaments would never have sharpened. Galaxies would never have condensed along their edges. You begin to see why cosmologists speak of voids not as mistakes, but as engines of structure. They're the universe's quiet architects, shaping the form of everything by their expansion. Yet of course, even this neat model has its complications. Some physicists propose that the universe's foamy texture might echo deeper physics from the Big Bang itself. Theorists studying inflation, the brief explosive expansion that set everything in motion, suggest that tiny quantum fluctuations in the primordial vacuum may have stretched into the seeds of today's voids. Others wonder whether the bubbles we see might mirror a larger cosmic truth, that even space-time could be a foam, fluctuating at the smallest scales. Historians still debate whether that bridge between large-scale and quantum foam was first seriously proposed by John Wheeler in the 1950s, or only later popularised by Hawking and others. Either way, the resonance between the very large and the very small is hard to ignore. You let your imagination run wild for a moment. If you could somehow stand outside the universe and look at it whole, it might resemble a glimmering cluster of soap bubbles, each void a hollow cell, each filament a bright boundary where light collects. The largest structures, like Laniakea or the Shapley supercluster, would appear as thicker ridges between bubbles. The image would shimmer, fluid, almost alive, and then as expansion continues, the bubbles would grow, merge and pop, reshaping the web entirely. Even cosmic architecture has an expiration date. What's especially fascinating and slightly humbling is that our own local void is growing. Observations show that it's expanding faster than the average universe, about 1.5 times the global Hubble rate. The more it expands, the more it influences the motion of surrounding galaxies. In another few billion years, it will be significantly larger, pushing its walls farther apart, thinning the filaments near us even more. Eventually, our corner of the universe may become even quieter, lonelier. Galaxies that now glow on our cosmic horizon will slip beyond visibility, swallowed by the dark. The bubble we call home will stretch toward transparency, and yet you find a strange peace in that image. The universe has always been a process, not a product, a dance of expansion and collapse, presence and absence. The cosmic bubbles rise and fade, but for now, we're inside one, able to look around, to map its shape, to marvel at its silence. Maybe that's all existence is meant to be, a momentary perspective inside a cosmic shimmer. The thought makes you chuckle softly. You could almost imagine the universe sighing, saying, "Relax, it's only foam," and you, small speck of consciousness drifting on its surface, whispering back, "Thanks for the view." You stay suspended inside that cosmic foam for a long moment, the bubbles glistening around you like transparent lanterns. But curiosity is restless. It wants to know why the bubbles form the way they do, whether our local void and its neighbours are inevitable products of cosmic physics, or simply coincidences frozen into place. To answer that, you drift not deeper into space, but into the digital universes that scientists have been building for decades. They call them cosmological simulations, vast experiments in mathematics where galaxies, voids, and filaments come alive inside computers. And through them, you can almost watch the universe dream itself into existence. The process begins with equations, specifically Einstein's general relativity combined with the fluid dynamics of dark matter and gas. Cosmologists seed their simulated universe with a nearly uniform mist, then add tiny random fluctuations, like the faint speckles of density left by quantum ripples in the early cosmos. They press go, and gravity takes over. Matter starts to clump, voids begin to inflate, and after billions of simulated years, the screen fills with something that looks uncannily familiar. A sprawling three-dimensional web of light and darkness, nearly identical to the one we observe through telescopes. It's as if nature and mathematics were reading from the same blueprint. Historians still argue whether the first true large-scale simulation deserving the title digital universe was the Millennium Run of 2005 or its predecessor, the Hubble Volume Project of the late 90s. Both modelled billions of particles of dark matter, tracking how gravity sculpted them into filaments and voids. What astonished everyone wasn't just the beauty, but the accuracy. The distribution of galaxies in those simulations matched the patterns seen in real sky surveys almost one-to-one. The cosmic web, it seemed, emerged naturally from the physics of gravity alone. You picture the hum of those supercomputers, rooms filled with blinking lights and cooling fans, machines crunching through quadrillions of calculations per second. Inside them, time moves millions of times faster than it does outside. In a few days of computation, they can age a virtual universe by 13 billion years. Every new run adds nuance. Gas cooling, star formation, black hole feedback, even radiation from exploding supernovae. It's as though each simulation is a rough draft of reality, each one refining our understanding of how something so immense can rise from nothing. The simulations confirm one thing clearly: voids aren't accidents. They're the natural byproducts of gravity and expansion. Where matter was slightly denser, it pulled more mass toward it. Where it was slightly less dense, expansion won the tug of war, evacuating the region. Over cosmic time, the dense regions grew into filaments and clusters, while the empty zones inflated like balloons. The local void isn't unique, it's just one of many hollows produced by the same simple rules, repeating across scales like a fractal. Here's your quirky tidbit. One group of researchers at the University of Zurich nicknamed their simulation the universe in a coffee cup, because the volume of data required to model even a small cosmic patch fit into a few terabytes, about the digital equivalent of what's stored on a handful of coffee shop Wi-Fi routers. The phrase stuck. Now it's a running joke that you can order a cappuccino and a cosmos to go. Watching those simulations feels strangely intimate. You see galaxies forming at the intersections of dark matter filaments, each one igniting like a spark where cosmic winds collide. You see voids swelling between them, stretching like soap bubbles as matter drains away. Sometimes two voids merge, forming supervoids hundreds of millions of light years across. It's slow motion on a divine scale, a ballet with gravity as choreographer. You realize that emptiness isn't just leftover space, it's active, expanding, reshaping the web as it grows. Historians still debate how accurately these simulations reproduce the real local void. Some models predict a smoother, more spherical hollow, others show the messy, lopsided shape we actually observe. The discrepancies hint at unknown physics, perhaps variations in dark energy behavior or interactions between dark matter and ordinary matter that we haven't yet nailed down. Every mismatch between simulation and observation becomes a clue, a whisper that our understanding is still incomplete. You think of the scientists staring at their simulated universes on monitors late at night, adjusting parameters, running new iterations. There's something almost monastic about it. A devotion to creation, but one made of algorithms instead of prayers. Each run begins with nothing. No stars, no galaxies, just noise, and ends with structure so intricate it could make you cry. You imagine them watching the first filaments form, murmuring softly, "There it is, the web." The simulations also reveal something subtle about time itself. When you zoom in on a void region and let the simulation evolve, you notice that clocks there seem to tick differently. Expansion within an underdense region happens faster than average, so from the void's perspective, cosmic time runs just a bit ahead. The difference is tiny, fractions of a percent, but it's real. Living near the edge of a void means inhabiting a slightly younger, faster expanding slice of the universe. We're literally in a hurry compared to denser neighbourhoods. It's one of those details that makes you grin at the absurdity of scale. Entire eons of human civilization might pass before that clock difference adds up to a single second. Some simulations push the idea further, asking what would happen if dark energy weren't uniform but varied across space. In those digital universes, voids expand at wildly different rates, creating a patchwork of cosmic regions aging at slightly different tempos. It's like a galactic jazz ensemble, each void improvising its own rhythm, the whole cosmos swaying to a beat we can only faintly perceive. You take comfort in that image. Even the largest emptiness isn't truly empty. It's alive with motion, subtle and continuous. Every particle of dark matter in those virtual universes moves in quiet obedience to gravity's mathematics, and yet together they create something that feels organic, almost breathing. The simulations, for all their digital precision, remind you that reality itself is dynamic, an ongoing computation written in the language of physics. As you drift away from those glowing monitors in your mind, you realise that the line between experiment and art has blurred. The scientists who run these simulations are both coders and composers, orchestrating entire universes to understand the one they live in. And though their machines may hum instead of sing, what they produce is pure cosmic music, the harmony of order emerging from the infinite noise of nothing. You linger near the hum of those digital universes, he says, letting the simulated galaxies spin in your imagination. But beneath the elegance of the cosmic web, an unease stirs, a quiet suspicion that maybe our models aren't as complete as we think. Every simulation begins with assumptions, and one of the biggest is that most of the universe's mass is made of something invisible, dark matter. For decades, that idea has held everything together, literally. But the local void and the odd motions of galaxies around it keep poking holes in the story. Maybe, just maybe, the darkness we blame for cosmic structure isn't a thing at all. Maybe it's a misunderstanding. You start where the idea began. In the 1930s, Swiss astronomer Fritz Zwicky studied galaxies orbiting within the Coma cluster and found they were moving too fast to be held together by visible stars alone. He calculated that some unseen mass, what he called Dunkel materia, must be providing extra gravity. Decades later, Vera Rubin confirmed a similar mystery inside individual galaxies. Stars at their edges spun just as quickly as those near the centre, defying Newtonian predictions. The conclusion seemed inescapable. Something invisible was adding mass, outweighing ordinary matter by roughly a factor of 5. Since then, dark matter has become the scaffolding of cosmology. Simulations, gravitational lensing maps, and the cosmic microwave background all depend on it. But here's where the local void complicates things. If the universe's invisible matter is smoothly distributed through space, then voids should contain some of it, just less than average. Yet certain observations hint that our local void might be emptier than models allow, even in dark matter. That's not supposed to happen. Gravity should resist such deep underdensities unless the underlying physics behaves differently than we think. Historians still argue whether the first major challenge to standard dark matter thinking came from Mordechai Milgrom's 1983 proposal of modified Newtonian dynamics, MOND, or from later relativistic extensions like TeVS in the 2000s. Either way, these alternative theories suggest that maybe we don't need dark matter at all. Maybe gravity itself changes its behaviour at extremely low accelerations. In that case, the void's peculiar dynamics, its galaxies moving faster away from the centre than predicted, could be evidence of a subtle gravitational twist rather than missing mass. You imagine trying to measure that twist. Astronomers observe the peculiar velocities of galaxies around the void, watching how they accelerate away from it, and compare the motion with simulations that assume normal gravity. The fit is decent, but not perfect. Some galaxies move just a little too fast, as though the emptiness behind them is more empty than the equations allow. In those small deviations lies the entire debate. Are we misjudging the invisible matter? Or is space-time itself playing by slightly different rules? Here's your quirky tidbit. In the early 2010s, a group of astronomers held a workshop called Dark Matter and Other Missing Things, complete with t-shirts printed with the slogan, "Maybe it's MOND." Attendees still tease each other about it at conferences. Even in the most serious of fields, humour seeps through. It has to. When you're debating the fundamental nature of the universe, a joke or two keeps you sane. Back to the local void. Some studies of dwarf galaxies at its boundary show that they rotate in ways not perfectly predicted by dark matter or halos. Their outer stars move slower than expected, as if the gravitational influence drops off too gently. For supporters of modified gravity, that's music to their ears. For dark matter loyalists, it's an invitation to refine models. Maybe the halos aren't spherical, maybe feedback from star formation reshaped them. The two camps meet in the middle, each convinced that a better dataset will settle the question. Historians still argue whether such datasets can ever truly decide, since both theories can often be tweaked to mimic each other's predictions. You can almost see the cosmic courtroom scene, dark matter sitting in the witness chair, invisible and silent, while physicists argue over its guilt or innocence. One side waves simulations as evidence, the other points to anomalies in rotation curves. Meanwhile, the universe itself remains serenely unconcerned, expanding at its own pace. Dark matter, if it exists, is made of something not yet detected, a particle that interacts through gravity but barely at all through light or electromagnetism. Experiments buried deep underground and in Antarctic ice have searched for decades, waiting for a rare collision that might reveal its presence. So far, nothing. Each null result tightens the leash on what dark matter could be, not weakly interacting, not strongly self-annihilating, maybe not even a particle in the traditional sense. You can't help but wonder if the local void itself might be a clue. If it truly lacks the predicted share of dark matter, perhaps whatever fills the cosmos isn't a smooth fluid, but something more exotic, an emergent property of space-time, or even a kind of gravitational memory or gravitational memory effect. Some theorists have begun to describe dark matter not as substance but as curvature, the geometry of how time and space respond to the distribution of energy. It's as if the universe remembers where matter once was and keeps bending long after it's gone. You find that idea strangely poetic, gravity haunted by its own history, emptiness shaped by echoes. If that's true, the local void might not just be a gap in matter, but a residue of ancient motions, a cosmic scar where gravity still remembers an imbalance that no longer exists. Of course, not everyone buys that. The majority of astrophysicists still stand firmly with the dark matter camp because the models work astonishingly well on large scales. They explain the cosmic microwave background, galaxy clustering, lensing statistics, all of it. But even the faithful admit that something's missing. If dark matter is real, it must be found, not just inferred. Until then, it's a placeholder, a ghost in the equations. You look out across the void again, wondering whether that ghost truly fills the darkness, or whether the darkness itself is the ghost. Our misunderstanding of gravity masquerading as a thing. The universe doesn't answer, of course, it rarely does. Instead, it hums quietly, letting you choose your faith in matter unseen or in laws unperfected. Either way, the local void keeps expanding as if smirking at your indecision. Whatever drives its emptiness, particles, geometry, or misunderstanding, it keeps on doing its job. And perhaps that's all you need to know. The universe doesn't require you to believe in its mechanisms. It just keeps growing, quietly proving that something, somewhere is pulling or not pulling exactly as it should. You drift through that quiet courtroom of cosmic theories, the echo of debate still lingering in the vacuum when you sense motion again. Not the grand sweep of expansion, but the gentle streaming of galaxies sliding through the cosmic landscape. It's subtle, almost invisible, yet it defines everything. These flows are how the universe breathes. You feel them all around you, long, patient rivers of matter gliding along the filaments between clusters, bending and turning where gravity and emptiness compete. Astronomers call these immense migrations cosmic flows, and the local void, our cosmic hollow, plays a crucial role in directing them. Imagine it from a bird's-eye view. Galaxies are not scattered randomly but moving like leaves on vast currents of space-time. The densest regions, the clusters, act as gravitational basins. The voids, by contrast, act like highlands, regions where the cosmic water of matter drains away. You and the Milky Way sit somewhere between, on a slope that leads downwards toward the gravitational centre of the Laniakea supercluster, while the local void expands quietly behind, pushing you from the other side. The balance of those two influences, pull from density, release from emptiness, defines our cosmic trajectory. Back in the mid-20th century, astronomers thought galaxies simply moved with the overall expansion of the universe, like raisins riding the dough as it rises. But as measurements improved, they found peculiar velocities, tiny deviations from the smooth Hubble flow. Some galaxies drifted faster than expected, others lagged behind. The pattern wasn't random. Historians still argue whether the first convincing map of these motions came from the Cosmic Flows 2 project in 2010 or the later Cosmic Flows 4 update a decade later. But either way, those surveys revealed a striking fact. The Milky Way and its neighbours are not just expanding away from everything. We're flowing towards something. The numbers are staggering. Relative to the cosmic microwave background, our local group is moving at about 630 kilometers per second toward the direction of the constellation Centaurus. That motion isn't caused by any single mass, but by a network of attractors, the Virgo cluster, the Great Attractor, and beyond that the even larger Shapley concentration. Meanwhile, on the opposite side of us, the local void expands at roughly 260 kilometers per second, effectively pushing us forward. The combination gives our galaxy's drift its peculiar speed and direction, a cosmic dance of push and pull. Here's your quirky tidbit. One astronomer once compared this to surfing the gravitational tide, which inspired a group of graduate students to design t-shirts reading "Laniakea Surf Club, Catch the Flow." The shirt sold out at a physics conference. Somewhere out there, serious cosmologists are probably still wearing them under their lab coats, quietly proud of being intergalactic surfers. But behind the humour lies a genuine mystery. These cosmic flows trace the underlying distribution of matter, including dark matter, and so they serve as one of our best tools for mapping the unseen. When astronomers chart how galaxies move, they're essentially drawing the gravitational topography of the universe. The deeper the well, the stronger the pull, the broader the void, the faster the expansion within it. By combining thousands of velocity measurements, researchers can reconstruct the three-dimensional shape of both visible and invisible structures, like reading a landscape through the way rivers run. Still, the data don't always fit cleanly. Some galaxies near the void move faster than gravity alone predicts. Others seem oddly resistant to its expansion. Historians still argue whether these discrepancies point to errors in distance measurements or to new physics entirely, perhaps interactions between dark matter and dark energy that subtly alter motion at large scales. Every new survey refines the map, but the edges of knowledge shift as fast as the galaxies themselves. You picture those maps now, delicate filaments of blue and red arrows indicating motion toward and away, the void behind us shaded in pale grey like a ghostly lung expanding. The local group sits near the rim, arrows pointing outward, streaming into the denser regions ahead. To see it drawn like that is to feel motion as something tangible, a current carrying you and everything you know across billions of years. You realise you've never been still, not for a single moment. Not you, not your planet, not even your atoms. At human scales, those numbers are meaningless. 600 kilometres per second. You can't feel it, can't measure it in the tick of a clock or the sweep of a sunrise. Yet it defines our cosmic address more profoundly than longitude or orbit. Every photon that reaches Earth, every gravitational tug on the Milky Way's stars, is shaped by that slow, inexorable drift through space-time. If galaxies could feel wind, we'd feel it on our faces right now. Astronomers sometimes describe these large-scale patterns as velocity fields, a phrase that sounds technical but hides quiet poetry. A field implies continuity, a gentle fabric rather than discrete dots. The galaxies don't jump from one point to another, they slide. When two flows meet, they create boundaries, walls, filaments, and nodes. When flows diverge, they carve voids. The entire universe is built on these patterns of movement, and the local void is one of the biggest sources of divergence known nearby. It's not just an empty place, it's an engine that sculpts direction itself. You imagine what will happen in the far future. As dark energy continues to accelerate expansion, the cosmic flows will stretch thinner. Galaxies now connected by mutual gravity will drift apart until their motions freeze, isolated in silence. The local void will have done its work, pushing, guiding, shaping, and then it too will fade into the general emptiness. One day, distant descendants, if any remain, may see only the Milky Way merged with Andromeda, drifting alone, unaware that they once belonged to a magnificent flow, stretching across hundreds of millions of light years. For now, though, you can still feel it, if only in imagination. The cosmic tide, the pull of clustered gravity ahead, and the gentle push of void behind. It's a strange comfort, knowing that even in vast nothingness, motion persists. The universe has currents, and you are adrift within them. A small traveller carried by forces older than stars. You might never sense their touch, but they shape every sunrise, every orbit, every breath. And as you close your eyes, you can almost picture it. The local void exhaling, the galaxies gliding outward, and you, the tiniest speck of awareness, floating perfectly in the middle of that invisible wind. You've been watching the cosmic current carry galaxies across impossible distances, and now you start to wonder what it feels like to live inside one of those vast hollows. Not physically, since there's no air or friction to feel, but in the deeper, stranger sense of time itself. Because here's the quiet secret of the universe. Time doesn't flow the same everywhere. Clocks in dense clusters and clocks in cosmic voids tick at slightly different rates. Gravity, that patient sculptor, not only shapes space but also bends the rhythm of time. Inside a void like the one you call home, time moves just a bit faster. you're not just floating through emptiness, you're living in the cosmic fast lane. The effect is tiny, almost impossible to notice without precision instruments, yet it's real. Einstein's general relativity predicts that the weaker gravity is, the faster time passes. In dense regions where matter crowds together, space curves sharply and time runs slow. In empty regions, the curvature flattens, freeing clocks to tick a fraction of a percent quicker. On human scales, the difference is meaningless. Over billions of years, it becomes profound. A galaxy at the centre of the local void might experience the universe as being a few tens of millions of years older than a galaxy deep inside a cluster-like coma. In cosmic terms, voids are the early risers. They see the dawn first. Historians still argue whether the first to recognise the time-slip of voids was the British cosmologist George Ellis in the 1970s, or later theorists who formalised it through inhomogeneous cosmology models like the Lemaitre-Tolman-Bondy LTB framework. Either way, the concept rewrote how we think about the cosmic clock. The universe's expansion, it turns out, isn't perfectly uniform in a time. The rhythm depends on where you listen. That realization brings us to one of cosmology's more unsettling possibilities. What if part of the universe's apparent acceleration is just this local difference in tempo? If time runs faster in underdense regions like ours, then distant supernovae, observed through the lens of our faster clock, might appear to fade differently than expected. The universe could seem to speed up simply because our void-based perspective measures a slightly different beat. The thought feels mischievous, as if the cosmos has been hiding the truth behind a relativistic trick of timing. Of course, most cosmologists believe dark energy still drives the expansion, not our position in a void. Yet the cosmic clock effect refuses to vanish from the conversation. Papers still appear proposing that large-scale inhomogeneities could mimic or amplify the signatures of dark energy. Historians still argue whether these ideas belong in mainstream cosmology or in the realm of clever thought experiments, but the debate persists. The universe, it seems, enjoys keeping its accountants guessing. Here's your quirky tidbit. In 2012, a physicist humorously suggested that if you lived inside a massive void long enough, you'd age better than your denser universe counterparts. Cosmic fountain of youth, courtesy of gravitational time dilation in reverse. No one's lining up to test the theory, it would take several billion years, but it's comforting to know that technically our galaxy is aging just a whisper slower than the deepest cosmic vacuum. You can almost imagine the local void as a spa for time itself, where seconds stretch and wrinkles smooth out across epochs. You pause and let that sink in. Living in a faster ticking region doesn't change your daily life, but it does shift how you think about cosmic history. If time flows unevenly across the universe, then the age of the cosmos isn't a single number. It's a patchwork, some regions slightly ahead, some slightly behind, all woven together into the grand narrative of expansion. The Big Bang wasn't a simultaneous explosion everywhere. It was a wave that unfolded unevenly through space-time, still rippling today. Astronomers use the cosmic microwave background, CMB, as the universe's master clock, a record of the moment light first broke free 13.8 billion years ago. But even the CMB bears scars of the voids and clusters it passes through. Photons climbing out of gravitational wells lose energy, shifting slightly toward red. Those passing through expanding voids gain energy, shifting toward blue. The result, called the Rees-Seymour effect, subtly distorts the CMB's uniform glow. When scientists map those tiny temperature variations, they're not just seeing the early universe, they're seeing echoes of the present, the fingerprint of how voids like ours continue to shape time's texture. You think about your own clock, sitting somewhere on Earth, counting seconds that depend on both local gravity and cosmic context. The tick of every watch, the swing of every pendulum, the oscillation of every atom, all are entangled with the curvature of space-time. It's humbling to realize that your heartbeat, your breath, even your thoughts move slightly faster or slower depending on where in the universe you are. Time isn't a river with a single current. It's a delta splitting and rejoining across the topography of existence. Philosophers used to ask whether time would exist if nothing moved. Now you can ask whether time would flow the same if emptiness itself moved differently. Inside a cosmic void, expansion is motion. Space stretches faster here. And with that stretching comes the quickened pulse of the universal clock. You live in a region where time runs more freely, an odd privilege in a universe so dominated by gravity's grip. You smile at the irony. Humans worry endlessly about running out of time, yet, cosmically speaking, we're in the one neighbourhood where time gives us a little extra. Not much, just a handful of cosmic heartbeats, but enough to make the math beautiful. In the far future, as the void continues to expand and galaxies drift farther apart, that time differential will grow. Distant observers, if any remain, will see the universe through different rhythms, each isolated bubble aging to its own tempo. The grand cosmic symphony will dissolve into solos, each void keeping its own metronome, and perhaps that's fitting. In the end, the universe is not a clock at all. It's a choir of ticking hearts, each keeping time to its own gravity. You let the idea settle like dust in sunlight. Here, at the edge of the local void, you're a little ahead of time and a little behind understanding, suspended in a faster present that belongs only to this small, quiet corner of the cosmos. You float inside that slower spinning moment, aware that time itself hums differently here. And another thought sneaks in. What if all of this, the void, the flows, the cosmic drift, is telling us less about the universe and more about ourselves? There's a danger hidden inside every discovery, the same one that tripped philosophers long before telescopes existed, the anthropocentric trap. You look outward and see patterns, and somehow you always end up at the centre. We once placed Earth at the middle of everything, then the Sun, then the galaxy. Now, even when we claim humility, we keep wondering whether our corner of space is somehow special. Maybe it is, but maybe that instinct says more about human nature than about cosmology. It's an ancient reflex. When Copernicus shifted the centre of the solar system, people didn't just lose a coordinate, they lost comfort. Each scientific revolution since has repeated that dislocation. We are smaller, we are later, we are ordinary. Yet here we are again, whispering that maybe our cosmic address is unique after all. The local void, after all, is unusually large. The Milky Way's neighbourhood is oddly quiet. The conditions that gave rise to life here are delicate. Historians still argue whether this instinct to interpret special circumstances as purpose first crept into science through the anthropic principle of the 1970s, or through older theological echoes smuggled in by habit. Either way, the temptation remains strong to see meaning where there may only be measurement. You imagine two astronomers staring at the same data. One sees a fluke, the other significance. The first says, "We live in an underdense region because probability allows it." The second replies, "We live here because only such regions permit observers like us." Both are technically correct. The first statement describes how, the second speculates why. The anthropic principle doesn't so much explain the universe as it explains why we can ask questions about it at all. If intelligent life requires a long stretch of cosmic stability, then of course it will appear in a calm suburb like ours, not in the gravitational chaos of galaxy clusters. We notice the void because we evolved in its quiet. Here's your quirky tidbit. At a 2009 cosmology conference, someone printed badges reading "Anthropic Reasoning, because we're here to argue about it." Delegates wore them proudly, half in jest, half in surrender. The universe might not revolve around us, but our debates certainly do. You pause and let that irony expand. Living near a void doesn't necessarily make us privileged, it might simply make us possible. Dense regions overflow with radiation, supernovae, and gravitational collisions. Spectacular, yes, but hostile. The local group's relative isolation gave Earth billions of peaceful years for chemistry to turn into consciousness. If the universe were a city, we'd be the folks who built a library in a quiet district rather than a nightclub downtown. There's comfort in that perspective, not chosen, merely fortunate. Historians still argue whether anthropic thinking clarifies or contaminates cosmology. Some claim it's a tautology. Of course the universe's conditions allow observers, otherwise we wouldn't be here. Others defend it as a guardrail against arrogance, a reminder that every measurement carries our bias like a watermark. Even the question why this void hides a bias. It assumes purpose, direction, a reason beyond randomness. Yet randomness, on a cosmic scale, has a rhythm all its own. Voids form because statistics demand them. The dice of gravity were rolled and emptiness won this patch. You think about the word special, it sounds comforting, but in physics, it's a warning label. Anytime the data suggest we occupy a special position, it means something's off in our interpretation. The Copernican principle, The idea that we are not privileged observers remains the foundation of cosmology. Every time we forget it, the universe gently reminds us by proving us wrong. The irony, of course, is that discovering the void seems to place us right back in the centre of strangeness. We aren't central in space, but we are perched in an oddly quiet frame of reference, watching everything else rush away. The cosmic suburbs again, ordinary in every way except for how lonely it feels. You smile at that. Maybe loneliness is the price of consciousness. The universe's silence gives us the room to think, and thinking inevitably turns inward. The anthropocentric trap isn't just scientific, it's psychological. When faced with emptiness, the mind paints its own reflection on the dark. We project significance the way stars project light, unconsciously, inevitably, beautifully. Imagine stepping outside the galaxy for a moment, seeing the Milky Way hanging over the rim of the local void. From that vantage, your sense of self evaporates. You're no longer the observer. You're a fleeting pattern of atoms or us, nested inside another pattern of stars. The question why here loses its sting. The universe isn't singling you out, it's just large enough to contain every possibility, including this one where you happen to exist. Yet even that humility loops back to wonder. Because if consciousness can arise here, on the edge of a vast hollow, then the void isn't empty after all, it's fertile in its own strange way. It has produced awareness capable of naming it. You are the void's self-portrait, drawn in starlight and thought. You picture scientists comparing maps of large-scale structure, arguing over statistical significance while somewhere a human heart beats faster under a dark sky. Both acts are the same impulse to find meaning in distance. The anthropocentric trap may never close completely because it's built into the act of observation. To measure the universe is to insert yourself into it. So you make peace with the paradox. You are not central, yet you are the centre of your own perspective. You live in an ordinary galaxy on the edge of an extraordinary void. You study the universe, and the universe studies itself through you. Maybe that's the quiet deal we've struck with the cosmos. We get curiosity, it gets awareness. In that exchange, even emptiness finds purpose. You glance once more toward the dark gulf beyond the Milky Way. It doesn't look like privilege anymore, it looks like possibility. The void isn't telling you that you're special. It's whispering that you're capable of noticing, and that in a universe this vast might be miracle enough. You drift in that humble stillness for a moment longer, the realization of your own smallness wrapping around you like a soft blanket, but when the light begins to shift. Not the light of stars, but an older, fainter glow, the afterimage of creation itself. You turn your attention toward the cosmic microwave background, the ghostly radiation that fills all of space, a low murmur left behind when the universe was only 380,000 years old. It is the oldest light you can see, and it's everywhere, seeping from every direction with near-perfect uniformity. Yet even this ancient glow carries secrets about where we live. Somewhere within its faint ripples, hidden among the static, may lie the fingerprint of our local void. The cosmic microwave background, or CMB as astronomers call it, is a kind of baby photo of the universe. When the cosmos cooled enough for electrons and protons to combine into atoms, light was finally free to travel without constant scattering. Those photons have been moving ever since, stretched into microwaves by the expanding universe. When scientists map them, they find tiny variations in temperature, differences of just 1 part in 100,000 that trace the seeds of all later structure. The bright spots mark slightly denser regions that became clusters and galaxies. The dark patches became voids. Even at its infancy, the universe already carried the blueprint of emptiness. Historians still argue whether the first hints of these anisotropies were truly seen by the Kobe satellite in 1992, or only confirmed in stunning detail by WMAP a decade later. Either way, those missions proved something crucial. The universe's large-scale structure, the cosmic web of filaments and voids, was encoded in those minute temperature ripples. The CMB is the fossil record of gravity's first whispers. Now imagine those ancient photons making their long journey to Earth. On their way, they pass through clusters, filaments, and voids. Each structure leaves a faint mark. When light falls into a gravitational well, it gains energy, then loses it again, climbing out. But in a universe still expanding, the balance shifts slightly. As a photon passes through an expanding void, space itself stretches underneath it, and the photon emerges with a tiny boost of energy, a blue shift so faint it's almost impossible to detect. This phenomenon, known as the integrated Sachs-Wolf (ISW) effect, allows astronomers to study the influence of voids and dark energy on the CMB. Here's your quirky tidbit. The first time scientists tried to detect the ISW effect caused by voids, their signal was so small that a skeptic joked it was like trying to hear a spider sneeze in a hurricane. Yet, years later, with better data from the Planck satellite, that sneeze turned out to be real. By stacking observations of known voids and superclusters, astronomers found subtle temperature imprints, hotter or colder spots corresponding to where photons had crossed those vast regions. The local void might be too close and too irregular to leave a strong mark, but its cousins farther away do. When you look at the CMB map, the pattern looks like mottled orange and blue camouflage. The largest structures ever detected in the universe, supervoids and superclusters, correspond to faint cold and warm spots only tens of microkelvins apart. Yet these tiny differences tell an enormous story. They hint that dark energy, the mysterious force accelerating cosmic expansion, is at work even on the largest scales. Without dark energy, the ISW effect wouldn't appear at all, but it does faintly, like a cosmic pulse still echoing through space-time. Some researchers have even searched for a specific signature, the so-called cold spot, a particularly large and unusually chilly region of the CMB discovered in WMAP data. At first, it looked like a statistical fluke, a random quirk of cosmic noise. But then surveys of galaxies in that direction revealed something intriguing. An enormous underdensity stretching billions of light years, now known as the Eridanus supervoid. Historians still argue whether that alignment is coincidence or correlation. But if the void really does cause the cold spot, it means we can see the gravitational shadow of emptiness imprinted on the oldest light in existence. You think about that for a moment, how emptiness can leave a mark on light older than galaxies. It's a comforting paradox. The void, though defined by absence, still has presence. Its gravity, or lack thereof, subtly reshapes the energy of passing photons. The local void does the same on a smaller scale, bending the motions of nearby galaxies, perhaps even tugging at the CMB itself in whispers we haven't yet separated from noise. Astronomers sometimes describe these interactions as light echoing off nothing. Photons travel for billions of years, interacting only with geometry, the shape of space-time carved by matter and vacuum alike. It's strange poetry. Light converses with darkness and comes away changed. When those ancient photons finally reach your detectors, they carry with them a history of everything they've passed, every void and cluster, every expansion and contraction. The CMB is not just an image of the past, it's a record of the journey. Historians still debate the precision of that journey. Some claim the local void's influence might help explain small asymmetries in the CMB, slight differences in power between hemispheres or subtle anomalies in alignment. Others argue those irregularities are artifacts, coincidences born from data processing. The conversation swings between mathematics and wonder, but the allure remains. What if the faint fingerprints of our cosmic neighbourhood are written on the face of the primordial sky? You gaze at that sky in your mind's eye, a soft microwave glow suffusing the entire universe, older than stars, older than time as we understand it. Somewhere within it, hidden in the temperature ripples smaller than your imagination can feel, is the memory of the void you live beside. The photons from the dawn of creation crossed its emptiness, and in doing so carried forward a trace of it. Even silence leaves an echo, and as you drift in that thought, you realize that the universe remembers everything. Light forgets nothing. The CMB isn't just a relic of what was, it's a diary of every place it's been. The local void, though invisible to your eyes, exists within that diary. A quiet, marginal note written in the ink of microwaves. You, reading it billions of years later, are simply the latest pair of eyes to glance across its pages. You stay there for a while, gazing at that ancient glow until it begins to fade in your mind's eye. When the light finally dims, something stranger takes its place, a suspicion, faint but persistent, that maybe all of this, the void, the web, the galaxies, might not be the full story. Because whenever science draws a map, imagination begins to colour beyond the edges. And so tonight, as you float between the local void and the faint hum of the cosmic microwave background, You begin exploring the alternative realities that have gathered, like satellites around modern cosmology. They are not official doctrines, just thought experiments. Wild, sometimes heretical attempts to answer what might be hiding behind the nothing. One of the oldest of these ideas is the multiverse, the notion that our universe is just one bubble in an infinite sea of others. In that picture, each bubble is a self-contained cosmos with its own laws of physics, expanding within a larger inflationary foam. Historians still argue whether this idea first crystallized in Andre Linde's eternal inflation papers of the 1980s, or whether it had already appeared in poetic disguise in Hugh Everett's Many Worlds interpretation of quantum mechanics decades earlier. Either way, the metaphor fits disturbingly well with what you've already learned. We live inside a bubble surrounded by others we can never reach. The local void could be a hint, a microcosmic echo of that same structure, a small bubble nested within a cosmic foam of universes. You imagine that for a moment. The local void as a tiny reflection of the universe's birth mechanism, a miniature bubble expanding inside a much larger bubble. The same mathematics that describe cosmic inflation can, in principle, describe how voids grow. Each emptiness pushes against its neighbours, each boundary becomes a thin wall of matter. If inflation happened infinitely, then somewhere beyond the horizon, countless other local voids might be swelling, each birthing its own galaxies, each with its own definition of normal. Somewhere out there could be a version of you wondering whether their void means something too. Here's your quirky tidbit. A 2016 cosmology conference held a mock debate titled Bubble Trouble, in which one team defended the multiverse and the other argued that our universe is strictly solo. The multiverse team brought balloons, inflating them on stage until the room was filled with floating universes. The host concluded the event by popping one with a laser pointer, declaring, "There goes Universe 47B." Science, it turns out, can have a sense of theatre, but the multiverse isn't the only alternative whispering through the void. Another idea, the cosmic texture hypothesis, suggests that the large voids and cold spots we see might be scars left by ancient topological defects in space-time itself. According to this theory, the early universe, as it cooled from its high-energy birth, underwent phase transitions like water freezing into ice. In the process, it may have trapped imperfections, knots, strings, and domain walls that warped the surrounding cosmos. Some physicists think that one of those defects could explain anomalies like the Eridanus cold spot in the cosmic microwave background. If true, then the local void might not just be a region of underdensity. It could be a bruise left by the universe's violent youth. Historians still argue whether such defects were ever directly testable. Most cosmologists now consider them rare, maybe even non-existent, since the latest sky surveys show no unmistakable gravitational signature. But the possibility lingers, partly because it's so evocative, that space-time itself can scar. That emptiness can remember trauma. If that's true, then every void, including ours, carries a faint echo of the universe's earliest convulsions, a cosmic birthmark stretching across millions of light years. And then there's the even stranger speculation, the simulation argument. You've heard it whispered often enough. What if the universe is a computational construct, a kind of cosmic simulation running on incomprehensible hardware? At first glance, it sounds like philosophy dressed in science fiction, but the deeper you look, the harder it is to dismiss entirely. In 2003, philosopher Nick Bostrom formalized the argument. If any civilization ever becomes capable of simulating entire universes with conscious inhabitants, and if they have reason to do so, then statistically it's more likely we're inside a simulation than in the original reality. The local void in that framework could be an artifact, a region of low data density, a cosmic render gap where the simulation's resolution drops. You smirk at the absurdity, yet something about the idea refuses to die. Even physicists occasionally toy with it. In 2017, a group proposed searching for grid patterns in high-energy cosmic ray distributions, as though reality's texture might reveal its pixelation. No one found anything, but the thought lingers in the late-night edges of theoretical conversation. Maybe the voids are simply the universe's way of saving on processing power. Every simulation needs empty space to stay efficient. And yet, for every exotic theory, a quieter truth hums underneath. The local void is strange enough without resorting to alternate universes or cosmic programming. It's a real measurable structure, proof that even the ordinary universe still holds mysteries vast enough to spark myth. You don't need another universe to feel small, this one does the job perfectly. Still, you understand the impulse. Whenever science reaches a limit, imagination steps in to keep the story going. Historians still argue whether these fringe hypotheses distract from genuine cosmology or expand its horizons. The truth probably lies somewhere in between. After all, many ideas once labelled fringe, like continental burst drift film, or even the existence of other galaxies, eventually became mainstream. The border between speculation and discovery is a moving target, shifting with each new observation. Perhaps the next great revolution in cosmology will begin once again with someone daring to ask a question that sounds ridiculous. You think of how every myth humanity ever told started with the same question: what's beyond the edge? For ancient sailors, it was the horizon. For cosmologists, it's the cosmic microwave background, the last wall of light before the unknown. Maybe beyond that lies another universe, or just a silence so complete that even light forgets its name. The local void in its stillness feels like a practice run for that ultimate horizon, a smaller infinity reminding you that every boundary, no matter how vast, invites curiosity. You let the possibilities swirl in your mind, multiverses bubbling like champagne, ancient scars warping space-time, digital gods debugging cosmic code. You don't need to believe any of them to feel their beauty. They're thought experiments wearing the clothes of wonder, proof that science and imagination share the same heartbeat. In the end, maybe that's what the void really teaches, that when faced with nothing, the mind creates everything. And so you float there between the real and the possible, surrounded by speculation as bright as galaxies. The local void hums quietly behind you, indifferent to all your theories, and somewhere deep down you know that's the point. The universe doesn't care whether it's simulated, scarred, or infinite. It just is. The rest is your story to tell. You're still adrift in that cloud of speculation, bubbles of multiverses, cosmic scars, digital dreamscapes. But as the glitter of possibility fades, something quieter rises to the surface. You find yourself wondering not about the universe's mechanics, but about its meaning. What does it feel like to live inside a huge void? Not in the astrophysical sense, but in the human one. The local void may be millions of light years wide, but somehow it echoes in the hollows of your own thoughts. You start to sense that this story, this vast geography of nothing, has always been a mirror for loneliness, curiosity, and the fragile hope that meaning can survive in a place so large it barely notices us. Philosophers have been circling this theme long before astronomers named it. Blaise Pascal, staring into a far smaller universe in the 17th century, confessed that the eternal silence of these infinite spaces terrifies me. The silence he felt then is the same one you feel now, magnified by telescopes and datasets. The local void simply gives that sepulchral a measurable size. And yet, unlike Pascal, you don't have to fear it. You can listen to it instead. Silence, after all, is not absence. It's the background against which everything sings. It's hard not to see a metaphor forming. The cosmic web resembles the human mind, bright nodes of thought connected by filaments of memory, with wide, dark voids in between. Maybe consciousness too depends on its own emptiness, pauses between sparks, spaces where meaning can gather. Historians still argue whether this comparison is mere poetry or whether it hints at something deeper, but either way it comforts you. If the universe can be structured around nothingness and still create everything beautiful, maybe the same is true for you. The local void also invites a strange sort of humility. To realize that your entire civilization exists at the edge of a giant hollow is to understand that you're not just small, you're peripheral, but that very marginality gives you perspective. Standing on the rim of emptiness lets you see farther. Had we been buried in a dense cluster, our sky might be crowded with galaxies so bright they drown out the rest. Instead, the void gifts us darkness, and through that darkness, clarity. We can see the universe because there's so little around to block the view. The emptiness that isolates us is the same emptiness that reveals everything. Here's your quirky tidbit. In 2015, a group of psychologists studying cosmic awe found that when participants looked at large-scale images of the universe, they reported feeling simultaneously smaller and more connected, a paradox they called the overview effect of cosmology. It turns out that staring into nothing can make you kinder. You realise your troubles are microscopic, yet somehow that smallness breeds empathy rather than despair. The void doesn't erase significance, it resizes it until it fits comfortably in the cosmos. You think of how human culture has always turned vast emptiness into metaphor. Desert monks sought enlightenment in isolation. Poets stared into winter skies to find stillness. Sailors crossed black oceans chasing discovery. Every tradition has its void, and each one teaches the same lesson. Emptiness is not the enemy of meaning, but its stage. Without the quiet, there can be no song. The universe, it seems, learned that long before we did. Historians still debate whether the very concept of a void owes more to ancient philosophy than to modern physics. The Greeks argued endlessly about whether true nothingness could exist. Aristotle said no, nature abhors a vacuum. Centuries later, quantum theory proved him half right and half wrong. Even the emptiest space still fizzes with virtual particles, tiny fluctuations popping in and out of existence. So even the local void, that enormous cavern of near nothing, isn't truly empty. It hums faintly with potential, the same way your own mind hums with possibilities even when it feels blank. The cosmos and the psyche share that restless stillness. There's also a certain irony in calling it a void. Language fails us here. The term suggests absence, but what you're really seeing is the presence of pause. The way gravity and expansion weave together to create structure. Without voids, galaxies would have nowhere to grow. Without pauses, thought would have nowhere to rest. The void is not a hole in the universe, it's part of its architecture. It's the space between notes that lets the melody exist. You can almost feel that philosophy settle into your bones. The local void becomes less a location and more a lesson. That existence depends on what isn't there as much as on what is. Your galaxy spins, your planet orbits, your cells divide, all of it framed by absence. And in that frame, you find not fear, but serenity. Maybe Pascal was only half right. The silence of infinite space isn't terrifying, it's tender. It's the universe giving you room to think. Imagine sharing this thought with someone far in the future, when the sky has gone dark and other galaxies have drifted beyond sight. They'll live in a universe even lonelier than yours, but they'll still ask the same questions. Where did we come from? What fills the dark? Why does emptiness feel so familiar? The answers will still point back to the same truth, that awareness itself is the universe's way of keeping company with its own vastness. You take a slow breath and picture the local void not as a wound in space, but as a mirror. It reflects everything, your curiosity, your insignificance, your desire to belong. You realize that you don't stand apart from the void, you stand within it. You are part of the same geometry that balances light and dark. To live here is to participate in the universe's most ancient conversation, the one between being and nothingness. And as that thought unfolds, something gentle happens. The fear drains away. The void doesn't look hostile anymore. It looks like home. The realization that the void feels like home lingers in your chest, soft and steady. You've traveled across billions of light years in thought, from the bright filaments of the cosmic web to the hush of the intergalactic dark, and somehow you've ended up here, back in your own small moments suspended between awe and understanding. But one question remains, glimmering at the edge of your imagination. What happens next? The void expands, the galaxies drift apart, the light thins. What does the universe become when its own structure begins to fade? And what does it mean for you, living inside this slow unravelling? To answer that, you look forward in time, not by years or centuries, but by eras. Cosmologists divide the future of the universe into epochs. The first is the stelliferous era, the age of stars, which you're still living in now. It began about 150 million years after the Big Bang, when the first suns ignited, and it will last for trillions of years yet. During this vast epoch, galaxies shine, black holes feed, and voids continue to stretch between them. But even now, the seeds of the next era are growing. Stars burn their fuel, galaxies exhaust their gas, and the cosmic web thins. The local void, patient as always, will keep expanding, swallowing the surrounding filaments like a tide erasing footprints. Historians still argue whether our part of the universe will eventually merge completely with that growing emptiness, or whether gravitationally bound groups like the Milky Way and Andromeda, soon to collide, will resist it. What's certain is that in 100 billion years or so, most galaxies will have slipped beyond our visible horizon. Their light will redshift until it's stretched beyond detectability. The night sky will grow darker, quieter, lonelier. Future astronomers, if any remain, will see only the merged remnant of our local group and may never know that a larger cosmos ever existed. In that far future, the local void will not be a region within the universe. It will be the universe, as everything else recedes beyond reach. The thought is melancholy, but not tragic. It's just physics doing what physics does, expanding, cooling, forgetting. Even now, dark energy accelerates that forgetting, stretching space-time faster with every passing eon. The galaxies, carried on that tide, will one day become isolated islands of light surrounded by oceans of perfect dark. In that endless expansion, every observer will live at the centre of their own shrinking universe, just as you do now. The local void is only a preview, a small rehearsal for the ultimate solitude that awaits. Here's your quirky tidbit. When astronomer Lawrence Krauss described this far future in a lecture, he quipped that cosmology will end with the greatest act of false nostalgia ever, the universe missing itself. The line drew both laughter and silence, the kind that follows a truth too large to grasp. Imagine it, a cosmos filled with nothing but memory, where even memory fades because there's no one left to remember. And yet, maybe that's not the whole story. The universe has a habit of surprising us. Even emptiness has energy, and energy means possibility. Some physicists have speculated that quantum fluctuations within the vacuum could someday seed new universes, a rebirth born out of decay. Historians still argue whether this process, called quantum tunneling of the vacuum, is inevitable or fantastically improbable. But if it ever happens, the local void could become a cradle instead of a tomb, giving birth to another cosmos, its boundaries expanding into a new reality. The universe might never end, it might just keep reinventing itself through its own silence. You find something oddly comforting in that image. Emptiness isn't just an ending, it's also the condition for beginning. Every birth, from stars to galaxies to thoughts, starts with a kind of void. Maybe when the last light fades, the universe will pause, breathe, and then exhale another creation. In that sense, the void isn't death, it's intermission. The philosophical poets of the early 20th century used to write about the heat death of the universe, the point where all energy is evenly distributed and no work can be done, as a metaphor for human despair. But you don't feel despair. You feel wonder. Because even if the cosmos cools and the lights go out, it still tells a complete story, a perfect arc, from chaos to order, from brightness to silence, from being to nothing. Every moment you exist within that arc is a miracle of timing. You're here, right now, during the small glittering window when stars still burn and life can ask questions. The universe may be temporary, but its wonder is eternal in the only way that matters, inside consciousness. Historians still debate whether life can persist in some form, even after the stars fade. Some suggest that black holes could provide warmth for artificial civilizations orbiting close to their horizons. Others imagine beings of pure computation, existing within quantum fluctuations themselves, feeding on the last entropy gradients. These ideas hover between science and myth, but you can't help loving them. They prove that even as the cosmos trends towards silence, imagination keeps talking. You picture the final night, galaxies dim, the void stretches endlessly, and somewhere in that vast quiet, a single mind, human, alien, or something unimaginable, looks out and whispers, "It was beautiful." The local void will be there too, patient as ever, the same dark mirror it's always been. It began as a hole in space, but by then it will be the stage for everything that remains. A silence so deep it sounds like truth. And maybe, just maybe, that silence isn't the end, but the purest form of peace. When the universe finally rests, it won't vanish, it will simply exhale, returning all its borrowed light to the darkness that once gave it birth. The void will remain, calm and infinite, waiting for whatever comes next. And you, small flicker of awareness, will have been part of its story, one heartbeat in its endless expansion. Now, as you drift back toward your own moment in time, you understand that the void was never something to fear. It was a teacher, showing you the shape of everything by showing you what lies between. In the space between stars, between thoughts, between Between beginnings and endings, you find it, the quiet truth that even nothing can be full of wonder. And now, as all that cosmic motion slows to a hush, you find yourself back where we began, here, in the soft dimness of your room, listening to the sound of your own breathing, syncing with the distant heartbeat of the universe. The journey through the void fades like a dream at dawn. Galaxies that once flared brightly in your imagination now drift gently into the quiet. You can still feel their pull somewhere deep inside, but it's softened, blurred, like memory seen through fog. The local void, that vast hollow that seemed so intimidating at first, has become strangely tender in your thoughts. A dark cradle holding all that ever was and all that will be. Let your mind settle there for a while. Picture the Milky Way, still gliding along the boundary between light and nothing, stars turning slowly as they have for billions of years. Somewhere inside that spiral your planet spins, your pulse beats, and time keeps its gentle rhythm. The universe hums in every atom around you, even in the silence. You're part of that hum, not separate from it. Every breath you take stirs a little of that ancient starlight, and every exhale drifts softly into the same expanding space that carries galaxies apart. The distance between you and the void isn't measured in light years. It's only the thickness of awareness. The air in your room feels cooler now, quieter. Maybe you can hear the faint whir of a fan, or the muted city sounds outside. Let them blend together into a single background note, like the cosmic microwave background of your own world, faint, constant, reassuring. The universe might seem vast and indifferent, but in this moment it's intimate. It's here. The same physics that steers galaxies along filaments guides the rhythm of your heartbeat. The same silence that fills the local void fills the space between your thoughts. You've been part of the universe's story all along, you just needed the dark to hear it. The longer you linger, the slower the world seems to move. Even words stretch out, softer now, heavier. You can almost feel gravity itself growing gentle, inviting rest. Somewhere far away, a cluster of stars collapses into memory, and another begins to form. Creation and decay, always alternating, like breath in and out. The cosmos doesn't end, it sighs. And you, small and bright in your brief moment, are made of the same sigh. Close your eyes now, and let the emptiness become comfort. The void isn't a void anymore. It's space enough for everything to exist, including you. The darkness that frightened ancient minds, the silence that once terrified philosophers, is only the universe at peace. You're floating in it now, weightless, timeless, exactly where you need to be. Breathe in, let the stars gather behind your eyelids. Breathe out, feel the galaxies drift a little farther apart as they've always done. The story continues quietly, infinitely, and somewhere within all that stillness you rest.